Some places seem to exist outside the flow of history. The world around them changes. Civilizations come and go, but they remain, silent, weathered, and strangely untouchable. From the moment they were rediscovered, these ancient monuments began asking questions that no generation has completely answered. Not because they are hidden, but because they refuse to fit comfortably into what we believe the ancient world was capable of. Every broken column, every perfectly cut stone, every forgotten passage hints at knowledge that has outlived its creators. And perhaps that is the greatest mystery of all. The monuments survived, the people did not. But somehow, their unanswered questions still have the power to shape the way we see our own past. Northern Belize hides one of the strangest survivals in the ancient Maya world. Beside the dark waters of the New River Lagoon, Lamani rises from the rainforest like a city that refused to die. While most Maya capitals collapsed more than 1,000 years ago, Lamani continued to survive for over 3 millennia. And hidden beneath its towering temples and giant stone faces lies one of the most overlooked engineering mysteries in the ancient world. Unlike many Maya cities rediscovered through dramatic expeditions, Lamani was never completely forgotten. Local communities had known about the ruins for centuries, but systematic archaeological investigation only began seriously in the 1970s under British archaeologist David Pendergast of the Royal Ontario Museum. As excavations expanded, researchers realized they were not uncovering an abandoned ceremonial center like Tikal or Kupan. They were uncovering a city that had remained continuously occupied from around 1500 BCE until the 17th century CE, an urban lifespan of nearly 3,000 years. That timeline alone stunned archaeologists. Most major Maya lowland cities experienced severe collapse during the Terminal Classic period around the 9th century, likely caused by drought, warfare, ecological exhaustion, or political instability. Tikal's population may have fallen by more than 70% within decades. Kupan experienced rapid depopulation after years of deforestation and soil depletion, yet Lamani continued functioning long after surrounding regions declined. Even Spanish missionaries arriving in the 16th century found an active settlement still operating beside the lagoon. The first mystery was geographical. Lamani should not have survived. The city sits in a humid tropical environment with annual rainfall often exceeding 2,000 millimeters. The surrounding terrain is unstable, swampy, and vulnerable to seasonal flooding. In modern engineering, constructing large stone architecture on waterlogged sediment requires deep stabilization systems and careful load distribution. Yet the Maya builders of Lamani erected massive temples that still stand after more than 1,000 years of erosion, storms, root penetration, and seismic movement. Geological analysis revealed something unexpected beneath the structures. The builders had created layered foundation systems using compacted limestone gravel, dense clay, and organic fill materials arranged in alternating strata. This design appears to have dispersed weight while absorbing movement from soft ground beneath the city. In effect, the foundations behaved similarly to modern floating substructures used in unstable wetland environments. No written Maya records describe this technique, yet the physical evidence suggests the builders understood soil behavior with surprising sophistication. One structure in particular dominates the skyline, the High Temple. Rising approximately 33 meters above the jungle canopy, it remains one of the tallest surviving Maya structures in Belize. Archaeologists estimate that its construction required tens of thousands of tons of limestone blocks. But the region lacks large draft animals, iron tools, or wheeled transport systems capable of moving such weight efficiently. This creates a logistical problem that researchers still debate today. Experimental archaeology has shown that moving multi-ton limestone blocks manually through tropical terrain is extraordinarily difficult. The dense rainforest surrounding Lamanai would have dramatically slowed transport. Some researchers believe the Maya transformed the lagoon and river network into a hydraulic transportation corridor, effectively turning waterways into ancient cargo routes. Canoes capable of carrying several tons may have transported stone closer to the construction zones before human labor completed the process. Yet even with water transport, the organizational scale required remains staggering. The labor force itself raises more questions. To sustain projects of this magnitude for centuries, Lamanai needed stable food production, political coordination, and long-term resource management. Evidence suggests the city developed extensive wetland agriculture around the lagoon, possibly including raised fields and controlled water systems. Satellite surveys and sediment analysis indicate that portions of the surrounding swamp may have been engineered to improve farming efficiency during seasonal climate fluctuations. This may explain why Lamanai outlived other Maya cities devastated by drought. Paleoclimate studies conducted across the Maya lowlands reveal a series of major drought events between approximately 800 and 1100 CE. Some lasted decades. Reservoir-dependent cities suffered catastrophic decline as water systems failed. But Lamanai's location beside a permanent freshwater corridor may have provided resilience unavailable elsewhere. The city was not isolated from climate stress. It simply appears to have adapted better than most. Yet the most disturbing mystery at Lamanai is not its survival. It is the faces. Along one of the city's ceremonial structures stands the famous Mask Temple, where enormous stucco masks emerge directly from the architecture. These giant faces, believed to represent Maya rulers or deities associated with cosmic power, are among the most visually striking sculptures in the Maya world. Some stand several meters tall, with intricate facial contours, layered headdresses, and preserved structural detail that should not still exist. Because under normal tropical conditions, stucco should decay rapidly. Traditional Maya stucco was made primarily from lime plaster created by heating limestone at extremely high temperatures, then mixing the material with water and binding agents. In humid rainforest environments, this surface usually cracks, absorbs moisture, and erodes over centuries. At sites like Tikal, many exposed stucco decorations deteriorated heavily after long environmental exposure. Yet portions of the Lamanai masks retained remarkable stability even after more than 1,000 years. Chemical analysis of surviving plaster fragments revealed unusual composition patterns. Researchers identified differences in mineral ratios and traces of organic additives not commonly seen in standard Maya plaster recipes elsewhere in the lowlands. Some specialists suspect the builders may have experimented with locally sourced botanical compounds or modified lime processing methods to improve moisture resistance. If true, this would represent a level of material engineering rarely associated with ancient Mesoamerican construction. Even more mysterious is the structural adhesion of the masks themselves. Massive stucco surfaces attached to stone substructures in tropical heat and rainfall should gradually separate as expansion, contraction, and biological intrusion weaken the bonds. Yet several sections remained attached with astonishing durability. Some archaeologists compare the survival rate of these masks to Roman hydraulic concrete, which also achieved unexpected long-term resistance through highly specialized mineral chemistry. No definitive explanation exists. The orientation of the city introduces another layer of mystery. Unlike cities such as Chichen Itza, where astronomical alignment dominates architectural planning, several structures at Lamanai appear oriented toward the lagoon itself. Reflections of sunlight across the water may have played ritual roles during specific seasonal periods. Wind direction, water flow, and visibility corridors seem integrated into urban placement patterns. This suggests that Lamani's planners may have developed a combined environmental ceremonial system, one where hydrology and cosmology were fused into the architecture itself. Then came the metal discoveries. Excavations uncovered copper bells, metallic ornaments, and evidence of long-distance trade connections extending south toward Panama and Costa Rica. Metallurgy was relatively rare in the Maya world compared to civilizations farther south, yet Lamani appears to have participated in technological exchange networks that connected distant regions of Central America. Some copper artifacts discovered at the site date to periods when many Maya centers were already declining. This implies that Lamani remained economically connected, while neighboring systems fragmented. Trade may have been another reason for its longevity. What do you think made Lamani survive for nearly 3,000 years while so many other Maya cities collapsed? Was it advanced engineering, environmental adaptation, or something we still don't fully understand? Share your thoughts in the comments below. Perched on a prominent hill overlooking central Scotland near Bathgate, Cairnpapel Hill appears at first to be little more than a grassy mound surrounded by earthworks. Yet beneath the surface lies evidence of nearly 4,000 years of continuous ceremonial activity. Long before Stonehenge reached its final form, generations of people returned to this hilltop, reshaping it again and again. Archaeologists can identify the monuments they built, the graves they dug, and the structures they left behind. What remains difficult to explain is how prehistoric communities repeatedly demonstrated levels of planning, surveying, astronomical observation, and long-term knowledge preservation that seem remarkably sophisticated for societies without writing, metal instruments, or formal mathematics. The modern story of Cairnpapel began in the 1940s when large-scale excavations led by archaeologist Stuart Piggott revealed a sequence of monuments hidden beneath the hill. What appeared to be a single burial mound turned out to contain layers of construction representing multiple eras of prehistory. Excavations uncovered ceremonial circles, post holes, burials, stone settings, and later Bronze Age tombs. Each generation had modified the landscape while preserving the site's importance. Instead of a single monument, Cairnpapel emerged as a record of thousands of years of engineering decisions. One of the greatest mysteries concerns the selection of the hill itself. Cairnpapel rises approximately 312 meters above sea level and commands panoramic views across much of central Scotland. Modern digital terrain analysis shows that the location offers exceptional visibility over surrounding landscapes. Today, such position could be identified through satellite imagery, GIS software, and topographic surveys. 5,000 years ago, none of those technologies existed. Yet prehistoric builders somehow selected one of the most strategically prominent locations in the region. Researchers continue to debate whether this choice was purely symbolic or based on practical surveying knowledge. Similar questions arise at other major prehistoric centres such as Stonehenge in England and Newgrange in Ireland. In all three cases, builders appear to have selected locations possessing unusual visibility, horizon characteristics, or astronomical potential. Some archaeologists suggest that prehistoric surveyors may have developed sophisticated landscape assessment techniques that are poorly understood today. The challenge is that such knowledge would leave almost no direct archaeological evidence. The earliest phases of Cairnpapel included large circular arrangements marked by timber posts. Today, the wood has vanished completely, leaving only stains and post holes in the soil. Reconstructing these circles reveals a surprising degree of geometric regularity. The spacing between posts appears deliberate rather than random. Creating such layouts on uneven terrain without modern measuring tools would have required practical geometry. Experimental archaeologists have demonstrated that circles can be created using ropes and central reference points. However, this explanation raises additional questions. Rope-based geometry still requires standardized measurements, planning, and coordination. Someone had to establish consistent lengths and maintain accuracy across the entire construction process. Similar mysteries surround prehistoric circles across Britain, where builders repeatedly achieved impressive geometric precision centuries before formal mathematical texts existed in Europe. The construction of ritual pits at Cairnpapel presents another engineering puzzle. Excavations revealed deep features cut into the underlying geology. Digging such structures using stone, antler, and bone tools would have demanded enormous labor. Modern calculations suggest that even relatively small ceremonial excavations could require hundreds of work hours. Yet the pits were often placed with remarkable consistency relative to other features within the monument. This implies a level of planning extending beyond simple excavation. Builders appear to have understood how to organize labor, establish reference points, and maintain spatial relationships over time. Such capabilities resemble basic surveying practices found in much later civilizations. The tools were simpler, but the underlying principles may have been surprisingly advanced. Perhaps the most astonishing aspect of Cairnpapel is the continuity of construction across millennia. Archaeological evidence indicates that successive generations repeatedly built over earlier monuments. Timber circles gave way to stone settings. Ceremonial enclosures evolved into burial monuments. Bronze Age tombs appeared within areas already considered sacred for centuries. The time separating these phases was often hundreds of years. In some cases, entire cultural traditions had changed. Yet builders consistently retained awareness of important locations within the site. The central zones remained significant despite the passage of many generations. This creates one of the most difficult questions in prehistoric archaeology. How was knowledge transmitted across centuries without written records? Modern societies preserve technical information through documents, maps, and archives. Neolithic communities relied entirely on oral traditions. Somehow, information regarding sacred locations, construction layouts, and ceremonial practices survived for periods longer than the entire history, separating the Norman conquest from the present day. The geometric organization of Cairnpapel provides additional evidence of technical sophistication. Surveys indicate that many features conform to circular or near-circular arrangements. While modern observers often underestimate the difficulty of constructing accurate circles, engineers recognize that even simple geometry requires reliable reference systems. Comparisons with Stonehenge are revealing. Studies of Stonehenge suggest builders maintained alignment errors measured in only a few degrees despite transporting stones weighing up to 25 tons. Cairnpapel's structures were smaller, yet they display similar concerns with spatial order and symmetry. The recurring appearance of geometric planning across multiple prehistoric sites suggests that practical surveying traditions may have been widespread throughout Neolithic Britain. The most intriguing mystery, however, involves astronomy. Many researchers have investigated whether Cairnpapel's layout incorporates celestial alignments. Although consensus remains elusive, several features appear oriented towards significant points on the horizon. Certain alignments may correspond to sunrise or sunset positions during particular times of the year. Others potentially relate to major lunar standstills, rare astronomical events occurring approximately every 18.6 years due to the Moon's orbital cycle. If these alignments were intentional, the implications are extraordinary. Tracking lunar standstills requires observations spanning nearly 2 decades. No individual observation session could reveal the pattern. Instead, generations would need to record and remember horizon positions over long periods. This level of astronomical monitoring rivals achievements documented at sites such as Stonehenge, the Callanish Stones and Newgrange. Modern astronomical software allows researchers to reconstruct ancient skies. Some simulations suggest that horizon markers visible from Cairnpapel may have served as observational reference points. Yet proving intentionality remains challenging. Were these alignments deliberate engineering decisions or coincidental outcomes of construction? Archaeologists continue debating the evidence. Nevertheless, the possibility raises profound questions about prehistoric knowledge systems. Astronomy was not merely about observing the sky, it required measurement, memory, prediction, and communication. A community capable of tracking celestial cycles over decades possessed a form of scientific knowledge, even if it was never written down. The burials at Cairnpapel add another layer of complexity. During the Bronze Age, important graves were placed within the existing ceremonial landscape, often in central or symbolic locations. This suggests later communities still understood the site's earlier layout. Whether through surviving markers or cultural memory, such continuity points to effective ways of preserving knowledge across generations. In the hills of Tuscany, Italy, lie the ruins of Vetulonia, an ancient Etruscan city where enormous tombs, advanced metallurgy and sophisticated engineering emerged centuries before Rome dominated the Mediterranean. More than 2,500 years later, archaeologists can still see the results of its technology, but many of the methods behind it remain a mystery. Although known from ancient historical references, the true location of Vetulonia was lost for centuries. In the 19th century, archaeologist Isidoro Falci identified the site through systematic excavations that uncovered monumental tombs, rich grave goods, defensive walls, and evidence of a once powerful urban centre. What emerged from the soil was not merely a forgotten city, but one of the most technologically sophisticated settlements of the Etruscan world. The rise of Vetulonia was closely connected to one of the most important technological revolutions of the ancient Mediterranean, metallurgy. The city occupied a strategic position near the mineral-rich regions of southern Tuscany and maintained access to the iron deposits of Elba Island. Archaeological excavations have revealed weapons, tools, bronze vessels, jewelry, and industrial debris, indicating large-scale metal production. This alone is not surprising, as many ancient societies worked with metal, but what makes Vetulonia unusual is the consistency and quality of its products. Modern metallurgical analysis has shown that many Etruscan bronze artifacts contain carefully controlled proportions of copper and tin, requiring not only access to raw materials, but also a practical understanding of furnace behavior, temperature management, and alloy composition. Without thermometers, chemical laboratories, or written technical manuals, Etruscan metalworkers repeatedly produced durable alloys whose mechanical properties rivaled those of many contemporary cultures. When compared with early Iron Age communities elsewhere in Europe, Vetulonia appears significantly more advanced, with craftsmen operating within complex trade networks that stretched across the Mediterranean, connecting the city to Greek colonies, Phoenician merchants, Sardinia, and perhaps even regions farther east. Yet, despite the abundance of finished products, the manufacturing knowledge itself has largely vanished. Archaeologists can analyze the metal, but they cannot fully reconstruct the expertise that produced it. The most astonishing mystery of Vetulonia rises above the landscape in the form of gigantic tumulus tombs. Some of these burial monuments exceed 60 meters in diameter and contain internal chambers constructed from carefully arranged stone blocks, with famous examples such as the Tomb of the Pietrera and the Tomb of the Diavolino, demonstrating engineering capabilities that seem remarkably sophisticated for the period. At first glance, these structures appear simple, essentially giant artificial hills covering burial chambers, but the reality is far more complicated. A mound 60 meters wide can contain tens of thousands of tons of earth and stone, generating enormous pressure on the chambers beneath it. If the internal supports are insufficient, the roof collapses. If drainage is poorly designed, water infiltration weakens the structure, and if the foundation shifts, the entire monument may fail. Yet many of these tombs have survived for more than 25 centuries. Modern engineers recognize that maintaining the stability of such a system requires an understanding of load distribution and soil behavior, meaning the builders needed to predict how weight would move through the structure, prevent water accumulation, and ensure that the burial chambers remained stable beneath an artificial mountain. The mystery deepens when considering the available technology, as no steel reinforcement, concrete computer modeling, or modern geological surveys existed, yet the tombs remain standing. Comparable challenges can be seen in the burial monuments of Mycenaean Greece and the tumulus traditions of Northern Europe. But the Etruscan examples occupy a unique position, with their combination of scale, geometry, and longevity suggesting an empirical understanding of structural engineering that was never formally recorded, leaving the question of how this knowledge was acquired unanswered. Another puzzle emerges from the stone architecture itself, as many blocks used in Vetulonia's tombs and defensive structures display surprisingly accurate fitting. Although not as extreme as the polygonal masonry of Sacsayhuaman in Peru or the walls of Alatri in central Italy, the precision remains impressive. Researchers studying tool marks have identified evidence of systematic stone shaping, with builders repeatedly achieving straight surfaces, controlled angles, and stable joints despite working with relatively simple iron tools. The challenge becomes clearer from an engineering perspective, as producing a flat stone surface several meters long is difficult even today without proper measuring equipment, and maintaining geometric consistency across dozens or hundreds of blocks requires reliable standards of measurement. Yet no complete Etruscan technical texts describing surveying procedures have survived, leaving the buildings intact while the instruction manuals have disappeared. Excavations have gradually revealed that Vetulonia was not merely a collection of buildings scattered across a hillside, but a city that exhibits clear evidence of planning. Roads connect strategic sectors, residential zones interact with defensive structures, water management systems appear integrated with the surrounding terrain, and access routes were designed to exploit natural topography while maintaining communication throughout the settlement. This suggests organized surveying, as ancient surveyors faced the difficult task of measuring slopes, establishing alignments, calculating distances, and maintaining orientation across uneven ground, where even small errors could create serious problems for drainage systems, roads, and defensive walls. Although the Romans later became famous for such capabilities, Vetulonia demonstrates that sophisticated surveying traditions may already have existed among the Etruscans, raising unanswered questions about how accurate those methods were and how the knowledge was transmitted between generations. One of the least discussed mysteries of Vetulonia concerns water management, as every ancient city depended on controlling water, with excess rainfall capable of destroying roads, weakening foundations, and triggering erosion, while insufficient water threatened agriculture and daily life. The surrounding landscape of Vetulonia presented additional challenges due to its historical marshes and changing coastal environments. Archaeological evidence suggests that the inhabitants successfully adapted to these conditions, with drainage systems, road placement, and settlement planning appearing carefully coordinated. Modern hydrological studies show that even small mistakes in drainage design can produce catastrophic long-term damage, yet portions of the urban infrastructure survived for centuries, raising the fascinating possibility that ancient engineers possessed a practical environmental knowledge far more sophisticated than commonly assumed. What do you think? Did the engineers of Vetulonia possess practical knowledge far beyond what we currently understand, or have we simply lost the records that would explain their achievements? Share your thoughts in the comments below. Madauros was discovered by modern archaeologists in the highlands of northeastern Algeria near the modern town of Madaurok, roughly 100 kilometers south of the Mediterranean coast. Scattered Roman ruins had long been known to local inhabitants, but systematic investigations during the 19th and 20th centuries revealed something far more remarkable: the remains of a sophisticated city that flourished on the edge of the Roman Empire. Archaeologists uncovered a theatre, baths, temples, paved streets, reservoirs, and extensive residential districts. The structures themselves were impressive, but the deeper mystery emerged when researchers began asking a simple question: how did a large urban centre sustain itself in a region with limited water resources, variable rainfall, and no major river nearby? More than 1,700 years after its peak, Madauros continues to challenge historians because many of the engineering systems that supported urban life remain only partially understood. Madauros occupied an important position within Roman North Africa, a region that became one of the empire's most productive agricultural zones. During the first centuries CE, North Africa supplied enormous quantities of grain and olive oil to the city of Rome. Some estimates suggest that provinces across the region contributed millions of tons of agricultural products over several centuries. Yet, successful agriculture required stable infrastructure, reliable water management, and careful environmental adaptation. Madauros existed within this network, but unlike cities situated along major waterways, it depended on technological solutions that are still difficult to reconstruct in detail. The most significant mystery concerns water. Modern satellite imagery, excavation reports, and topographic surveys indicate that the city possessed large public baths, fountains, reservoirs, and drainage systems. Roman baths were extraordinarily water-intensive. Even a medium-sized bath complex could consume hundreds of thousands of litres of water per day. Cities such as Rome, Carthage, and Caesarea relied on massive aqueduct systems stretching tens or even hundreds of kilometres. Madauros appears to have achieved similar urban functions without access to such obvious natural advantages. Archaeologists have identified cisterns and evidence of water collection infrastructure, but the full hydraulic network remains unknown. Some researchers suspect that substantial portions of the system remain buried beneath later deposits or were dismantled during centuries of reuse. The surviving evidence demonstrates that the water arrived. What remains unclear is exactly how engineers guaranteed sufficient supply during prolonged dry seasons. This challenge becomes even more intriguing when compared with other ancient settlements. Petra in modern Jordan developed sophisticated runoff collection systems capable of capturing seasonal floods. The Nabateans transformed an arid landscape into a thriving urban centre through channels, reservoirs, and dams. Similarly, the inhabitants of Madauros appear to have mastered local hydrology, yet the precise methods used to balance seasonal variability remain uncertain. Unlike Petra, where many hydraulic structures remain visible, much of Madaros' infrastructure has disappeared, leaving only fragments from which researchers must reconstruct the larger system. Another unresolved question involves surveying technology. The city exhibits the characteristic planning principles found throughout the Roman world. Streets align with remarkable consistency. Public buildings occupy strategically organized locations. Drainage channels follow carefully calculated gradients. Today, engineers accomplish such tasks with GPS receivers, laser levels, and digital mapping systems. Roman surveyors relied on instruments such as the chroma and chorobots. These tools were ingenious but mechanically simple. Nevertheless, Roman cities across thousands of kilometers frequently achieved levels of geometric precision that continue to impress modern researchers. At Madaros, the layout suggests advanced understanding of slopes, water flow, and spatial organization. The mystery is not whether Roman surveyors were skilled. The mystery is how such accuracy was consistently achieved across generations with limited technology and without the mathematical frameworks used by modern engineering. The city's construction materials introduce another layer of uncertainty. Many surviving walls remain standing despite nearly 2 millennia of weathering. North Africa experiences significant temperature fluctuations, seasonal rainfall, erosion, and occasional seismic activity. Yet portions of Madaros continue to endure. This durability echoes one of the most famous technological puzzles of the ancient world: Roman concrete. Scientific studies published during the 21st century revealed that certain Roman concretes contained self-healing properties generated through chemical interactions involving lime clasts and mineral-rich aggregates. Researchers examining harbour structures in Italy have identified mineral formations that strengthened concrete over time rather than weakening it. While Madaros was not a coastal harbour, its surviving masonry raises similar questions. Did local builders adapt construction formulas to regional materials? How much practical knowledge was transmitted through apprenticeship systems that vanished centuries ago? Archaeologists can analyze the stones and mortar chemically, but chemical composition alone cannot fully explain the craftsmanship behind structures that survived far longer than many modern buildings. The theatre of Madaros presents a different kind of engineering mystery. Roman theatres were designed not only as entertainment venues, but also as acoustic machines. Many could project unamplified speech to audiences numbering in the thousands. Modern acoustic modelling has demonstrated that curved seating arrangements, stone surfaces, and architectural geometry can significantly enhance sound transmission. Yet no detailed engineering manuals survive explaining how local builders optimized these effects in every location. The theatre at Madaros follows principles seen throughout the Roman world, but each site required adaptation to specific terrain, materials, and environmental conditions. Whether builders relied on formal calculations, empirical experimentation, or generations of accumulated knowledge remains uncertain. Beneath the visible city lies another largely invisible system: drainage. Urban success depended not only on delivering water, but also on removing it. Excess rainfall, wastewater, and runoff had to be managed continuously. Archaeological evidence indicates the presence of underground drainage infrastructure integrated into the city's layout. Such systems required precise gradient control. Too steep and channels would erode. Too shallow and sediment would accumulate. Modern civil engineers solve these problems through mathematical modelling and fluid dynamics. Ancient engineers achieved comparable practical results through methods that remain imperfectly understood. The physical channels survive. The knowledge used to design them largely does not. Madaros also raises broader questions about environmental adaptation. North Africa today is often associated with arid landscapes, yet environmental evidence indicates that regional conditions fluctuated significantly over time. Ancient communities needed strategies for drought resilience, agricultural productivity, and resource management. The city's long occupation suggests successful adaptation across multiple generations. Similar challenges confronted settlements from the Levant to the Iberian Peninsula. Some failed, Madauros endured. Archaeologists can identify the outcome but still struggle to reconstruct the complete decision-making processes that enabled such resilience. In the humid lowlands of southern Mexico, near the San Pedro Mata River in the state of Tabasco, archaeologists uncovered the remains of Moral Reforma, a forgotten Maya city hidden beneath dense jungle and flood-prone wetlands. The site was first reported in the early 20th century, but major excavations only intensified decades later when researchers realized the city was far larger and more advanced than previously believed. Each excavation season revealed something new. Massive pyramids emerged from beneath layers of vegetation. Stone monuments covered in hieroglyphs identified rulers linked to powerful Maya kingdoms such as Calakmul. Later surveys uncovered plazas, elevated platforms, drainage systems, and evidence of large-scale engineering in terrain considered extremely unstable for monumental construction. What shocked researchers most was the location itself. Moral Reforma was not built on hard mountain bedrock like many famous ancient cities. It stood in a swampy river basin with soft alluvial soil, seasonal flooding, and annual rainfall exceeding 2,000 millimeters. Modern civil engineering often struggles in such terrain without deep reinforced foundations. Yet the Maya built pyramids more than 27 meters tall here over 1,200 years ago, and many structures still remain standing. That contradiction became the beginning of one of the most overlooked engineering mysteries in the ancient Americas. The greatest mystery surrounding Moral Reforma is how its builders stabilized enormous stone structures on terrain that should have collapsed under their weight. Geological studies around the site show high concentrations of clay, saturated sediment, and flood deposits. Such soil behaves unpredictably under pressure. In modern construction, engineers usually solve this problem using deep concrete piles or steel reinforcement. The Maya had neither. Excavations beneath several ceremonial platforms revealed layered construction methods, unlike ordinary Maya foundations. Archaeologists discovered alternating levels of compacted earth, crushed limestone, gravel, and organic material carefully arranged to distribute pressure across a broader surface area. Some researchers compare the concept to modern floating foundation systems used in wetland construction today. The engineering becomes even more impressive when considering the climate. Tabasco's tropical rains rapidly erode exposed surfaces. Many colonial-era structures built only a few centuries ago in nearby regions have deteriorated more severely than the much older Maya remains at Moral Reforma. Satellite imaging and LiDAR scans suggest the city may also have been artificially elevated over time through repeated layers of engineered fill. If correct, the Maya were effectively reshaping the landscape itself to create stable urban terrain in an environment naturally hostile to permanent architecture. This raises an uncomfortable question for historians. How much practical geotechnical knowledge did the Maya truly possess? The ancient city existed in a region where water was both life and threat. Seasonal floods could transform the surrounding terrain into a vast marshland within weeks. Yet Moral Reforma survived for centuries as a major political and ceremonial center. Archaeologists later identified traces of canals, embankments, reservoirs, and raised causeways extending around the urban core. Some channels possess gradients so subtle that modern researchers initially believed they could not have functioned effectively. yet sediment analysis indicates controlled water movement likely occurred through them for long periods. The system appears designed not only to drain floodwater, but also to regulate moisture levels across agricultural zones surrounding the city. This resembles hydraulic strategies seen at Angkor Wat in Cambodia, where vast reservoirs and canals supported dense urban populations centuries before modern hydrology. What makes moral reformer remarkable is scale versus technology. The Maya lacked iron tools, draft animals, and wheeled transport systems for heavy labor. Despite this, they created hydraulic infrastructure sophisticated enough to sustain urban life in one of the wettest regions of Mesoamerica. Some archaeologists believe the city's survival depended entirely on this engineered landscape. If even part of the water control network failed, flooding and agricultural collapse may have followed rapidly. Ironically, the same system that allowed the city to flourish may also explain its eventual disappearance. Another major mystery concerns the movement of construction material. The region around Moral Reforma contains limited high-quality building stone, yet the city's pyramids and stairways required thousands of tons of limestone blocks. Without horses, oxen, or industrial tools, the Maya somehow transported heavy material across swampy terrain and dense rainforest. Researchers estimate some blocks weighed several tons. Moving them even short distances would have required immense coordination. One theory proposes seasonal river transport. During flood periods, stone may have been floated on large rafts through interconnected waterways before being dragged across prepared earthen ramps. Another hypothesis suggests raised causeways functioned as engineered transport corridors capable of supporting concentrated human labor teams. But none of these theories completely explain the precision of construction found at the site. Certain staircases and retaining walls exhibit alignment errors of only a few millimeters. Some joints remain remarkably tight despite centuries of rainfall and soil movement. Comparisons have been made with masonry precision at Palenque, and even with certain Andean stonework traditions thousands of kilometers away. The difference is that Moral Reforma achieved this level of stability in unstable wetland conditions, where gradual shifting should have destroyed alignment long ago. Like many Maya cities, Moral Reforma appears connected to astronomical observation. Several pyramids and plazas align closely with solar positions during equinoxes and solstices. Researchers studying the site noticed that certain ceremonial structures frame sunrise angles with unusual precision. During specific times of year, sunlight passes directly through architectural corridors and illuminates key stairways or plaza entrances. Some scholars argue these alignments were symbolic only. Others believe the city functioned partly as a giant observational instrument integrated into the Maya calendar system. The Maya already possessed one of the most accurate ancient calendars ever created, calculating solar cycles with astonishing precision centuries before European mechanical astronomy. The question is not whether the Maya understood astronomy. The real mystery is how they achieved such accuracy without optical instruments. Aligning massive structures to celestial movements requires long-term observation, mathematical consistency, and intergenerational transmission of data. At Moral Reforma, these alignments may also have served political purposes. Kings could associate themselves with predictable cosmic events, reinforcing divine authority through architecture itself. For centuries, the jungle erased nearly all memory of Moral Reforma. Then excavations uncovered carved stelae containing royal inscriptions and political records. Each discovery changed historians' understanding of the city. One monument revealed alliances with larger Maya powers. Another described military conflicts and dynastic struggles. Later inscriptions suggested the city controlled important river trade routes, linking inland kingdoms with Gulf Coast regions. This transformed Moral Reforma from a forgotten provincial settlement into a strategic political center. Yet the inscriptions also deepen the mystery. If the city possessed advanced engineering, strategic trade access, and political influence, why was it abandoned so completely? Climate change remains one possibility. Paleoclimatic studies across the Maya world indicate severe drought cycles between the 8th and 10th centuries. But moral reforma existed in a wetland environment, making drought alone an incomplete explanation. Other researchers point toward political collapse, warfare, or failure of hydraulic infrastructure. If the water management system deteriorated, flooding could have rendered large sections of the city uninhabitable within decades. The jungle then finished what history began. At nearly 3,000 meters above sea level in Peru's Sacred Valley lies Pisac, an Inca site so precisely engineered that even today, scientists struggle to explain how its builders mastered mountains, water, and stone without modern technology. Spanish chroniclers recorded the ruins centuries ago, but systematic archaeological investigation only revealed their true scale in the 20th century. What initially appeared to be a fortress soon proved to be something far more complex. At first glance, Pisac looks familiar. Stone walls cling to mountain ridges, agricultural terraces cascade down steep slopes, and temples occupy commanding viewpoints overlooking the Sacred Valley below. To most visitors, the site appears to be another impressive Inca settlement. Yet the longer archaeologists study Pisac, the stranger it becomes. Many ancient sites contain mysteries involving a single monument, a particular building, or an unexplained artifact. But Pisac is different. Here the mystery extends across an entire mountain landscape, where every terrace, every channel, every retaining wall, and every carefully positioned structure appears to participate in a larger engineering system that remains only partially understood. The greatest mystery may not be the buildings themselves, but the mountain, because evidence increasingly suggests that the Incas transformed an entire mountainside into a giant engineered machine. The terraces are the most obvious feature, and thousands of visitors photograph them every year, as from a distance they appear to be simple agricultural fields carved into the slopes. However, closer examination reveals extraordinary sophistication. Modern excavations have shown that many terraces contain multiple engineered layers, with large stones forming the foundation, above which lies a drainage layer of gravel and smaller rocks, followed by additional layers of sand and fertile soil that complete the structure. This arrangement resembles principles used in modern civil engineering. The purpose was not merely to grow crops, as the terraces controlled water, stabilized slopes, prevented erosion, distributed moisture, and protected the mountain itself. Researchers studying Inca agricultural systems have estimated that some terrace complexes dramatically reduce surface runoff compared with natural slopes, allowing water during seasonal rains to penetrate downward through carefully designed layers rather than rapidly washing soil away. Remarkably, many of these systems continue functioning after roughly 5 centuries, whereas modern retaining walls frequently require maintenance after only decades. Pisac's terraces continue operating after hundreds of years of earthquakes, storms, and environmental change. How such durability was achieved remains unclear, as no surviving Inca manuals explain the calculations, no architectural blueprints have been found, and no written engineering instructions survive. Yet the results remain visible across the mountain. The question becomes even more intriguing when considering the terrain itself, as Pisac occupies one of the most challenging environments imaginable for large-scale construction. Steep slopes dominate the landscape. Altitude complicates labor. Heavy seasonal rains threaten stability, and gravity constantly attempts to pull entire sections of mountain downhill. Modern engineers facing such conditions rely on geological surveys, soil testing, computer modeling, and advanced measurement equipment. Yet the Incas possessed none of these technologies, at least none that archaeology has identified. Nevertheless, the terraces follow the contours of the mountain with astonishing consistency, and their geometry appears deliberate rather than improvised. Many align perfectly with natural formations, while simultaneously maintaining structural stability, suggesting a sophisticated understanding of geology, though the source of that knowledge remains uncertain. Water may represent the site's most impressive technological achievement, as across the ancient world, water management often determined whether civilization flourished or collapsed. The Romans built aqueducts, the Nabateans engineered Petra's hydraulic systems, and ancient Persians developed qanat networks extending for kilometers underground, yet the Incas followed a different path. Rather than forcing nature into rigid channels, they often designed systems that worked with the landscape itself, and Pisac demonstrates this philosophy on a massive scale. Archaeologists have identified channels, drainage features, and water control mechanisms distributed throughout the site, some of which remain only partially explored while others are hidden beneath later deposits. The visible elements alone suggest a complex network designed to regulate rainfall and protect infrastructure. But what remains unknown is how much of the original system still lies concealed underground. Many researchers suspect that substantial portions have yet to be discovered, and if true, then the engineering complexity visible today may represent only a fraction of the original design. The stonework introduces another layer of mystery, as like other major Inca centers, Pisac contains examples of exceptionally precise masonry. Some stones fit together so tightly that inserting even a thin blade between them is difficult, an observation often repeated but frequently underestimated in significance. Creating such joints requires more than patience, as it demands measurement, planning, and quality control. Each stone possesses a unique shape, many containing multiple angles and irregular surfaces, and a mistake on one contact point could affect every adjoining block, yet the finished assemblies often appear seamless. Comparisons with other ancient civilizations highlight the achievement. As Egyptian builders mastered monumental scale, Roman engineers excelled at arches and concrete, while the Incas specialized in precision fitting under seismic conditions. In earthquake-prone regions, rigid construction often fails, but Inca masonry appears to absorb movement while maintaining stability, leading some scholars to argue that this characteristic helped many structures survive earthquakes that destroyed later colonial buildings. However, the underlying methods remain debated, and exactly how the builders measured, tested, adjusted, and finalized these stone interfaces is still uncertain. The location of Pisac raises additional questions, as many structures occupy seemingly strategic positions overlooking valleys and mountain horizons. Some alignments may relate to astronomy, while others may connect to sacred geography, reflecting the Inca view of mountains, rivers, and celestial bodies as interconnected elements within a larger cosmological framework. Several researchers have proposed that certain architectural orientations correspond to solar events, seasonal cycles, or significant landscape features, and if these interpretations are correct, then Pisac functioned as more than an agricultural center. It may have served simultaneously as an observatory, ceremonial complex, administrative hub, and environmental monitoring system, a multifunctional design that would require extraordinary planning. Engineers would need not only to understand construction and hydrology, but also possess knowledge of astronomy, geography, and seasonal agriculture, making the integration of these disciplines one of the site's most fascinating aspects. Logistics create yet another unsolved puzzle, as every stone visible at Pisac had to be extracted, transported, positioned, and fitted into place, all at high altitude on steep terrain. The Incas possessed no wheeled transport system for large construction projects, lacked draft animals capable of moving massive loads comparable to oxen, and had no steel machinery, combustion engines, or hydraulic cranes. Yet monumental architecture emerged across the Andes, and Pisac joined sites such as Machu Picchu, Ollantaytambo, and Sacsayhuaman in presenting the same fundamental question: how did ancient builders repeatedly achieve results that appear disproportionate to their available tools? The answer remains incomplete, as archaeologists have proposed combinations of ramps, human labour, rope systems, and ingenious planning, which account for part of the process, though whether they explain everything remains open to debate. Nuku Hiva stone sites are scattered across the remote island of Nuku Hiva in the Marquesas archipelago of French Polynesia, more than 1,400 kilometers northeast of Tahiti in the Central Pacific. Their existence was known to local communities for centuries, but systematic archaeological investigation only accelerated during the 20th century as researchers began documenting the island's monumental stone platforms, ceremonial complexes known as meiai, massive retaining walls, terraces, and enigmatic tiki statues carved from volcanic rock. What archaeologists discovered was unexpected. On an isolated island with no metal tools, no wheeled transport, no draft animals, and limited natural resources, ancient builders created some of the most sophisticated stone constructions in Polynesia. The mystery is not whether these structures exist. They stand today across valleys and mountainsides. The mystery is how a relatively small island population developed engineering solutions capable of transforming one of the most rugged volcanic landscapes in the Pacific into a network of monumental architectural complexes whose construction methods remain only partially understood. The first challenge begins with geography itself. Nuku Hiva covers approximately 340 square kilometers and consists largely of steep volcanic terrain cut by deep valleys and dramatic cliffs. Modern visitors often struggle to reach many archaeological sites, even with contemporary roads and vehicles. Yet ancient builders somehow transported enormous quantities of stone across this difficult landscape. Excavations reveal ceremonial platforms extending dozens of meters in length and constructed from carefully selected basalt blocks, weighing hundreds of kilograms and, in some cases, multiple tons. Unlike the civilizations of Egypt, Mesopotamia, China, or Rome, the inhabitants of Nuku Hiva possessed neither iron tools nor complex machinery. They operated within what archaeologists classify as a non-metallic technological system. Nevertheless, they reshaped entire hillsides. The scale of landscape modification remains one of the greatest puzzles. Many meiai were not simply placed on naturally flat ground. Builders first transformed steep slopes into engineered terraces. This required excavation, leveling, drainage management, and the construction of retaining walls capable of resisting soil pressure and tropical erosion. Modern geotechnical engineers recognize that slope stabilization is among the most difficult forms of construction, because mistakes often result in landslides or structural collapse. Yet many of Nuku Hiva's ancient terraces have survived for centuries despite intense rainfall, tropical vegetation growth, earthquakes, and erosion. The achievement invites comparison with the agricultural terraces of the Inca in Peru or the mountain engineering of the Ifugao rice terraces in the Philippines. However, unlike those societies, the Marquesan builders left no written records explaining their methods. The retaining walls themselves present another technical mystery. Numerous structures employ dry stone construction, meaning no mortar binds the stones together. Instead, stability depends entirely on the selection, shaping, and placement of individual blocks. Archaeologists studying these walls have noted remarkably effective load distribution. Larger stones often form the foundation, while carefully fitted intermediate layers reduce stress concentrations. In some locations, the walls remain stable after hundreds of years of exposure to environmental forces. This durability is particularly surprising because volcanic islands experience repeated cycles of moisture expansion, root intrusion, and ground movement. Similar dry stone techniques appear in places such as Machu Picchu and certain Mediterranean fortifications, yet direct cultural connections are impossible. The resemblance suggests that different societies independently discovered advanced structural principles through observation and experimentation. Perhaps nowhere is ancient craftsmanship more visible than in the island's stone sculptures. Nuku Hiva contains numerous tiki statues carved from basalt, one of the hardest volcanic rocks commonly available to ancient peoples. Some statues exceed 2 meters in height and display symmetrical facial features, detailed anatomical forms, and stylistic consistency that implies highly skilled specialists. Experimental archaeology has attempted to replicate such work using stone tools comparable to those available to ancient Polynesians. Results indicate that carving even a single large basalt figure would require enormous labor investment and exceptional technical expertise. Yet multiple sites contain concentrations of statues that suggest production occurred on a scale larger than previously assumed. Researchers continue debating how artisans achieved such precision, how long individual sculptures required to complete, and how finished monuments were transported across difficult terrain. The transportation problem becomes even more intriguing when population estimates are considered. Before European contact, estimates for the population of the Marquesas vary widely, ranging from tens of thousands to perhaps over 80,000 inhabitants across the archipelago. Even under higher estimates, the labor required to quarry, transport, and assemble thousands of tons of stone represents a substantial organizational challenge. Modern construction projects rely on cranes, steel cables, vehicles, and surveying instruments. Ancient Marquesans relied on human coordination. This implies sophisticated social systems capable of mobilizing large workforces, allocating resources, and transmitting technical knowledge across generations. The architecture therefore serves not only as evidence of engineering, but also as evidence of complex administration. The mystery deepens when researchers examine the spatial distribution of archaeological sites. Rather than concentrating exclusively around a single political center, monumental structures appear across numerous valleys throughout the island. Surveys have documented extensive networks of ceremonial platforms, residential terraces, agricultural modifications, and stone monuments. This distribution suggests that engineering knowledge was not confined to a single elite workshop. Instead, expertise may have been widely shared among multiple communities. Such decentralization raises questions about how technical information circulated. Without writing systems, knowledge transfer depended entirely upon oral traditions, apprenticeship, and practical experience. Yet the consistency observed in construction techniques indicates surprisingly reliable transmission over long periods. Another unresolved question concerns surveying methods. Modern engineers use levels, measuring instruments, and mathematical calculations to establish horizontal surfaces and structural alignments. The builders of Nuku Hiva possessed none of these technologies in a modern sense. Nevertheless, many ceremonial platforms exhibit impressive geometric regularity. Walls remain straight over considerable distances. Terraces maintain stable elevations. Structural components align in ways that appear intentional rather than accidental. Archaeologists suspect the use of highly refined observational methods involving chords, sight lines, wooden markers, and accumulated practical experience. However, direct evidence for these techniques remains scarce because organic surveying tools rarely survive in tropical environments. Some researchers have also investigated possible astronomical dimensions of site planning. Polynesian navigators were among the greatest seafarers in human history, crossing thousands of kilometers of open ocean using observations of stars, ocean swells, winds, and bird behavior. The settlement of the Marquesas itself represents a remarkable technological accomplishment. Certain ceremonial complexes appear oriented towards significant solar positions or landscape features that may have held cosmological importance. While evidence remains debated, the possibility raises fascinating questions. If the same observational knowledge used for long-distance navigation influenced architectural planning, then Nuku Hiva's monuments may preserve traces of an integrated scientific tradition linking astronomy, ritual, and engineering. The maritime context may ultimately represent the greatest technological mystery of all. Before any stone platform could be built, people first had to reach one of the most isolated island groups on Earth. Genetic, linguistic, and archaeological evidence indicates that Polynesian voyagers traversed vast ocean distances long before European navigators entered the Pacific. Reaching the Marquesas required voyages of thousands of kilometers across waters lacking visible landmarks. Experimental voyages using reconstructed traditional canoes have demonstrated that such journeys are possible, but they also highlight the extraordinary navigational expertise required. In many ways, the stone monuments of Nuku Hiva may be secondary achievements compared to the maritime knowledge that brought their builders there. Eridu stands near the ancient floodplains of southern Iraq, where one of humanity's oldest and most mysterious cities emerged thousands of years before the pyramids of Egypt. Today, many archaeologists consider Eridu the first true city on Earth, and one of the greatest technological enigmas of the ancient world. Discovered through 19th and 20th century excavations led by Iraqi and British archaeologists, Eridu appeared at first to be little more than a desert mound. But beneath the sand were the remains of a civilization dating back nearly 7,000 years, older than the pyramids of Egypt and older than Stonehenge. What researchers uncovered there challenged long-held assumptions about how civilization began. For decades, historians believed cities evolved slowly from small farming villages. Eridu does not seem to follow that pattern. Archaeological layers suggest that sophisticated urban planning, large ceremonial architecture, water management systems, and organized labor emerged there surprisingly early. In many ways, Eridu appears less like the beginning of civilization and more like the remains of a society that already understood the fundamentals of engineering and centralized control. One of the greatest mysteries surrounding Eridu is its impossible location. Southern Mesopotamia was an unstable environment dominated by marshes, seasonal flooding, salt contamination, and extreme summer temperatures that can exceed 50 degrees Celsius. Even modern agriculture in southern Iraq struggles with soil salinity and water control. Yet around 5,400 BCE, the people of Eridu established a permanent settlement that survived for thousands of years. This should not have been easy. Ancient farmers faced a deadly problem in Mesopotamia. Irrigation slowly poisons the soil. As water evaporates under intense heat, salt remains trapped in the ground. Over time, farmland becomes infertile. Archaeologists studying Sumerian agriculture estimate that wheat production in some southern Mesopotamian regions eventually collapsed because salinity became uncontrollable. But Eridu endured far longer than many neighboring settlements. Excavations revealed traces of ancient canals and carefully engineered water channels surrounding the city. Some researchers believe the inhabitants developed one of humanity's earliest hydraulic management systems. The canals were not random trenches dug into mud. Their gradients appear carefully controlled, allowing water to flow while reducing stagnation and salt accumulation. A slight engineering mistake would have flooded fields or poisoned them permanently, yet the system functioned for centuries. What makes this more mysterious is the technological timeline. This was thousands of years before advanced mathematics, before iron tools, and before large surveying instruments. The people of Eridu may have relied entirely on practical experimentation, observation of seasonal water behavior, and inherited technical knowledge passed down through generations. Some archaeologists argue that southern Mesopotamian civilization was built not on military conquest, but on mastery of water engineering. At the center of Eridu stood another anomaly, a massive religious complex rebuilt again and again for millennia. Archaeologists uncovered at least 18 successive temple layers stacked directly on top of each other. Instead of demolishing older structures completely, the inhabitants preserved them beneath newer construction, gradually creating an elevated sacred platform. This process would later evolve into the famous Mesopotamian ziggurats. The strange part is the consistency. Across thousands of years, the sacred center remained aligned almost perfectly in the same location. The builders repeatedly maintained the orientation and proportions of the temple, despite different generations, political changes, and environmental shifts. Such continuity suggests the existence of a highly stable cultural or technical tradition. Some researchers speculate that early Sumerian priests may have possessed sophisticated observational systems tied to astronomy or geographic positioning. Ancient Sumerian texts later described Eridu as the city of the god Enki, deity of wisdom, water, engineering, and creation. In myth, Eridu was not merely a city, it was where divine knowledge entered the human world. To modern scholars, these legends may preserve cultural memories of a place where early technological breakthroughs transformed human society forever. But among all the mysteries of Eridu, one stands above the rest: the survival of its mud brick architecture. Most of the city was constructed using sun-dried mud bricks, one of the weakest building materials imaginable. Mud brick is vulnerable to rain, wind erosion, salt crystallization, and temperature fluctuation. Under harsh conditions, untreated mud structures can collapse within decades, yet parts of Eridu survived for nearly 7,000 years. This has become one of the most overlooked engineering mysteries in archaeology. Researchers studying ancient Mesopotamian bricks discovered that the builders of Eridu did not simply shape mud and leave it to dry. The bricks often contained carefully balanced mixtures of clay, silt, straw, reeds, and organic temper materials. These additives dramatically reduced cracking during drying and improved structural flexibility. In some samples, microscopic analysis revealed mineral compositions that helped resist salt damage, one of the greatest environmental threats in southern Iraq. The science behind this is remarkable. Straw fibers act similarly to reinforcement material in modern composite engineering. As mud dries and contracts, fibers distribute stress throughout the brick, preventing catastrophic fractures. Certain clay compositions also improve thermal stability, reducing expansion and contraction caused by brutal desert heat cycles. Modern experiments recreating ancient Mesopotamian mud bricks found that correctly mixed organic additives could increase durability several times over compared to untreated mud. But there is another layer to the mystery. Many Eridu structures were built in areas with high groundwater salinity. Salt crystals expanding inside porous materials normally destroy mud brick over time. Modern concrete itself can suffer severe degradation under similar conditions. Yet some Eridu foundations remained identifiable after thousands of years buried beneath sediment and exposed to environmental extremes. Engineers still debate how ancient builders optimized these materials so effectively without modern chemistry. Some specialists believe the people of Eridu achieved this through centuries of empirical refinement. Others argue that the consistency of the bricks suggests standardized production methods far earlier than expected in human history. Comparisons with later civilizations make the puzzle even stranger. Egyptian pyramids relied primarily on limestone and granite. Roman engineering depended heavily on volcanic ash concrete. But Eridu's builders worked with mud, arguably the least durable major construction material, and still created structures that endured across entire epochs of civilization. In terms of material survival relative to available resources, Eridu may represent one of the greatest achievements of ancient engineering. Archaeologists also uncovered evidence suggesting organized labor and centralized administration. Storage facilities, production zones, and ceremonial architecture imply a coordinated society capable of mobilizing workers on a large scale. This raises another difficult question. How was such complexity managed before writing fully developed? The earliest proto-writing systems in Mesopotamia emerged thousands of years later, yet Eridu already displayed signs of economic coordination. Some researchers believe the inhabitants used clay tokens and symbolic accounting systems to track grain, labor, and trade long before formal cuneiform writing appeared. If true, Eridu may represent the birthplace not only of cities, but also of administration itself. Trade may have played an equally important role. Southern Mesopotamia lacked many natural resources, including stone, timber, and metal ores. Yet artifacts found at Eridu suggest long-distance exchange networks connecting distant regions of the Persian Gulf and beyond. This implies that maritime travel and organized trade routes existed far earlier than once believed. Do you think Eridu was simply humanity's first city? Or evidence that ancient civilizations understood engineering far beyond what we normally imagine? Share your thoughts in the comments below. Andriake is an ancient harbour on the southwestern coast of present-day Turkey, near the famous city of Myra. At first glance, it appears to be another Roman port scattered with ruins along the Mediterranean. Yet beneath layers of silt and centuries of abandonment lies one of the most intriguing engineering mysteries of the ancient world. Archaeologists have uncovered evidence of a harbour that remained active for more than a millennium. Despite constant sedimentation, earthquakes, changing coastlines, and the logistical challenges of sustaining maritime trade on a massive scale. Even more puzzling, Andriake became a centre of an industry so technologically sophisticated that modern researchers still debate parts of its production process, the manufacture of Tyrian purple dye, one of the most valuable substances of antiquity. The rediscovery of Andriake emerged gradually through archaeological surveys around the ancient harbour basin and extensive excavations conducted during the early 21st century. What researchers expected to find was a typical Roman port serving nearby Myra. What they uncovered instead was an enormous commercial complex containing warehouses, docks, industrial facilities, cisterns, administrative structures, and evidence of specialized manufacturing activities that connected the Eastern Mediterranean to trade networks stretching thousands of kilometers. The first mystery appears before examining a single building. Harbors are fragile systems, rivers deposit sediment, storms reshape coastlines, sea levels fluctuate. Modern ports often require continuous dredging using heavy machinery to remain operational. Yet Andriake functioned for centuries in an environment that should have gradually buried its harbour facilities beneath layers of silt. Geological studies show that sediment accumulation along Mediterranean coastal environments can significantly alter navigable channels over relatively short historical periods. Similar problems affected famous ancient ports such as Ostia near Rome and Ephesus in western Anatolia, both of which eventually lost direct access to the sea because of sedimentation. Andriaca somehow maintained its maritime importance long after many comparable ports declined. The harbour basin raises difficult questions about ancient coastal engineering. Archaeologists can identify quays, breakwaters, and harbour installations, but they still struggle to reconstruct the full system that kept maritime traffic functioning. Some researchers suspect that periodic dredging operations occurred. Others suggest that natural currents may have been exploited through carefully selected harbour placement. The challenge is that evidence for such maintenance activities rarely survives. We see the final infrastructure but not the operational knowledge that sustained it. The result is a technological puzzle hidden beneath layers of sediment that accumulated after the harbour's decline. The scale of Andriaca's commercial infrastructure deepens the mystery. The most impressive surviving structure is the massive granary built during the reign of Emperor Hadrian. Stretching approximately 64 meters in length and containing multiple storage chambers, the building ranks among the largest Roman granaries preserved anywhere in the Mediterranean. Such facilities were not merely warehouses, they represented critical components of regional food security systems. Grain had to be protected from humidity, pests, fungal contamination, and temperature fluctuations. A single storage failure could threaten thousands of people. Modern engineers studying ancient storage architecture have noted the remarkable effectiveness of passive environmental control systems used by Roman builders. Thick stone walls moderated temperature changes. Ventilation openings encouraged air circulation. Internal layouts reduced moisture accumulation. Yet a significant question remains unresolved. How did ancient builders develop these designs without modern thermodynamics, humidity sensors, or structural modeling software? The granary demonstrates practical knowledge of environmental engineering that appears surprisingly advanced for its era. Similar principles appear in Roman facilities from Egypt to Britain, but Andriaca offers one of the clearest surviving examples. Water management presents another engineering puzzle. A major harbour required enormous quantities of fresh water. Sailors arriving after weeks at sea needed supplies. Warehouses required maintenance. Industrial activities consumed significant resources. Yet Andriaca occupied a coastal environment where freshwater availability was limited. Archaeologists have identified cisterns, reservoirs, channels, and collection systems designed to capture and store water. The sophistication of these systems suggests long-term planning rather than simple improvisation. Hydraulic engineering has often been called one of Rome's greatest technological achievements. Aqueducts carried water across valleys, pressurized pipelines supplied urban fountains, complex drainage systems protected cities from flooding. Andriaca appears to have incorporated elements of this broader hydraulic tradition while adapting to local environmental conditions. However, many components of the original network remain buried or destroyed, leaving researchers with only fragments of the complete system. The visible infrastructure hints at a larger technological landscape that has largely vanished. Yet none of these mysteries rivals the most extraordinary aspect of Andriaca: its purple dye industry. Few products in human history have carried the economic and symbolic value of Tyrian purple. Across the Roman Empire, purple garments became symbols of political authority, wealth, and imperial power. Certain shades were so prestigious that their use was restricted by law. Emperors wore purple. Senators displayed purple borders on their garments. The colour became associated with status throughout the Mediterranean world. The source of this extraordinary dye was astonishingly impractical. It came from marine snails, belonging primarily to the Murex family. Archaeological excavations at Andriaca have revealed enormous accumulations of crushed shells, providing direct evidence of industrial-scale production. Scientific estimates suggest that producing a single gram of high-quality purple dye could require processing thousands of mollusks. Some historical reconstructions indicate that tens of thousands of shells might be needed to create enough pigment for a single luxury garment. This is where the technological mystery begins. Researchers understand the broad outline of the process. Specialized glands were extracted from the snails. The material underwent controlled decomposition and chemical transformation. Exposure to sunlight triggered additional reactions that altered the pigment's color. Temperature, oxygen levels, processing duration, and environmental conditions all influenced the final result. However, reconstructing the precise ancient technique has proven remarkably difficult. Experimental archaeologists have attempted to recreate Tyrian purple production using surviving historical descriptions. The results are inconsistent. Small variations in processing conditions can produce dramatically different colors, ranging from blue and violet to reddish purple. Modern chemistry explains some of these reactions, yet ancient producers achieved remarkable consistency across centuries of production. This suggests the existence of highly specialized technical knowledge transmitted through generations of craftsmen. The puzzle becomes even more impressive when viewed from an industrial perspective. Imagine coordinating the collection of tens of thousands of marine snails, transporting them to processing facilities, extracting minute quantities of raw material, controlling complex biochemical reactions, and producing a luxury commodity valuable enough to travel across the Mediterranean. This was not a simple craft. It was a sophisticated manufacturing system operating without laboratories, digital instruments, or written industrial manuals. Comparisons with other ancient industries reveal how unusual this achievement was. Roman concrete relied on carefully selected volcanic materials. Egyptian glassmakers controlled temperatures exceeding 1,000 degrees Celsius. Chinese bronze casters mastered complex metallurgical techniques. The purple dye industry of Andriache belongs in the same category of lost technological traditions. The products survive. The exact operational knowledge largely disappeared. Which mystery of Andriache fascinates you the most? Let us know your thoughts in the comments below. Perched high above the rugged landscape of southern France, the fortress known as Château de Quéribus appears less like a conventional castle and more like a natural extension of the mountain itself. Rising dramatically from a narrow limestone peak in the Corbières range, the citadel stands at an altitude of more than 700 meters above sea level, dominating the surrounding valleys and distant plains. From afar, the structure seems almost impossible. Stone walls clinging to the summit of a jagged rock formation, exposed to wind, weather, and gravity for centuries. Historians often refer to Quéribus as one of the legendary citadels of the sky, a group of nearly inaccessible mountain fortresses that once marked the frontier between medieval France and the Kingdom of Aragon. Yet beyond its dramatic location and strategic importance, the castle also raises a series of intriguing questions about the technical knowledge and construction methods of the people who built and expanded it during the Middle Ages. The origins of Quéribus remain partly obscured by time. Historical references suggest that a fortress may have existed on the site as early as the 10th century, though the structure visible today largely dates to the 13th century, when the region became entangled in the turbulent history of the Cathar movement and the Albigensian Crusade. For a time, the castle served as one of the final strongholds of the Cathars, a Christian sect declared heretical by the Catholic Church. After the fall of nearby fortresses, Quéribus reportedly held out until the middle of the 13th century before eventually coming under royal control. The French crown then reinforced and modified the structure, transforming it into a border fortress that guarded the frontier with Spain for several centuries. Although its political role gradually diminished after the Treaty of the Pyrenees shifted the border southward, The architectural complexity and remarkable engineering of the site continue to attract historians, archaeologists, and engineers who seek to understand how such a structure could be built in such an extreme location. One of the first mysteries surrounding Keribus concerns the sheer difficulty of its construction site. The castle stands on a razor-thin ridge of limestone that drops steeply on several sides, leaving very little flat ground on which to build. Transporting building materials to such a height would have been a formidable task in the medieval world. Every block of stone, every beam of timber, every barrel of mortar had to be carried up winding mountain paths long before modern roads or machinery existed. Some researchers believe that builders quarried much of the stone directly from the mountain itself, shaping the fortress out of the very rock on which it stands. Others suggest that a system of wooden cranes, pulleys, and scaffolding may have been used to lift materials upward in stages. Whatever the precise method, the logistics alone would have required careful planning, coordination, and an understanding of structural balance that challenges common assumptions about medieval engineering capabilities. The defensive design of the fortress reveals another level of sophistication. Rather than imposing a rigid geometric layout onto the mountain, the builders shaped the walls to follow the irregular contours of the rock. The result is a structure that blends almost seamlessly with its natural foundation, as if the mountain itself had grown defensive towers and stone ramparts. Access routes were intentionally narrow and winding, forcing anyone approaching the castle to move slowly through a sequence of gates, stairways, and courtyards that could be easily defended. Such features reflect a deep understanding of topography and military strategy. By integrating architecture with the natural terrain, the designers effectively turn the entire mountain into part of the fortress, maximizing defensive strength while minimizing the need for massive artificial walls. Inside the castle, the most striking architectural space is the Great Hall located within the main tower. This chamber contains a central stone pillar from which 4 Gothic arches radiate outward to support the vaulted ceiling. The elegance of this structure is remarkable, considering the limited tools available to medieval builders. Each stone block forming the arches had to be cut with precise angles, so that the weight of the roof would distribute evenly through the pillar and into the rock below. The geometry required for such a vault is complex, relying on carefully calculated curves and load-bearing lines. When viewed from below, the arches appear almost effortless, yet they represent a sophisticated understanding of structural mechanics that would have been developed through generations of practical experience. Perhaps the most intriguing technical mystery of Keribus lies in the stonework itself, particularly in the traces left behind by the tools used to shape the blocks. Many of the stones forming the fortress walls display cutting marks that are strikingly consistent across large surfaces. The grooves and planes appear remarkably straight, with edges that meet at sharp angles and surfaces that remain unusually smooth despite centuries of exposure. For archaeologists examining these details, the stonework raises important questions about the technology available to medieval masons. Conventional historical explanations suggest that craftsmen used iron chisels, hammerstones, and wedges to split and shape limestone blocks. These tools were certainly capable of producing well-finished masonry, yet the level of uniformity observed in some sections of Keribus suggests a degree of control that seems surprisingly advanced for the era. The precision becomes especially noticeable when examining joints between adjacent stones. In several areas of the fortress, the blocks fit together so tightly that very little mortar is visible between them. The surfaces appear to have been carefully flattened so that each stone rests securely against its neighbor, distributing weight evenly throughout the wall. Achieving this level of accuracy would have required repeated measuring, trimming, and testing of each block before it was finally placed. Even a small misalignment could weaken the stability of the structure, especially in a fortress perched on a narrow summit exposed to strong winds. The builders therefore had to balance speed, precision, and structural safety while working under challenging environmental conditions. Some researchers have proposed that the masons working at Keribus may have inherited techniques passed down from earlier Roman or Mediterranean stone-cutting traditions. Others believe the precision reflects the high level of craftsmanship achieved by specialized guilds of medieval builders who traveled from project to project across Europe. Regardless of the explanation, the stonework demonstrates a mastery of material that continues to fascinate modern observers. When sunlight strikes the pale limestone walls, the subtle tool marks become visible, revealing the rhythm of countless hammer blows delivered centuries ago by craftsmen whose names have long been forgotten. The durability of the fortress further deepens the mystery. Despite standing atop an exposed mountain ridge for more than 700 years, Keribus remains remarkably intact. Its walls have endured relentless winds, storms, and temperature changes that would normally erode poorly constructed structures. The tight fit of the stone blocks, combined with the natural strength of the limestone and the stability of the underlying bedrock, appears to have created a building capable of resisting the forces of nature for centuries. In many ways, the fortress demonstrates how effective medieval engineering could be when combined with careful observation of natural conditions. Today, as visitors climb the steep path to the summit, the fortress still inspires awe. From the top, sweeping views stretch across the valleys of the Ord region, while the stone walls seem to rise naturally from the mountain itself. Beyond the dramatic scenery lies a deeper story of ingenuity, perseverance, and technical skill. The precisely cut stones, elegant Gothic vaults, and the seamless integration of architecture with the rocky peak suggest that the builders of Château de Keribus possessed remarkable engineering knowledge. More than a medieval fortress, Keribus stands as a testament to the craftsmanship of the masons who shaped each block by hand, high above the valleys of southern France. Their work transformed a jagged mountain peak into one of Europe's most striking fortresses, one that still leaves historians questioning the exact techniques and tools that made such precision possible. In your opinion, how were medieval builders able to cut and fit stone blocks with such remarkable precision on a steep mountain peak? Share your thoughts in the comments below. On the edge of Peru's coastal desert, nearly 200 kilometers south of Lima, stands a structure that should not look the way it does. More than 5 centuries after the fall of the Inca Empire, the walls of Tambo, Colorado still display traces of red, yellow, and white pigments. In one of the driest regions on Earth, the colors remain. The question is simple: how? Spanish chroniclers recorded the site shortly after the conquest of the Inca Empire in the 16th century. Systematic archaeological investigations began centuries later, revealing one of the best preserved administrative centers ever discovered along the coastal branch of the Inca road system. Most ancient painted structures share the same fate. Time erases them. The brilliant blues of ancient Egypt faded, the painted temples of Greece lost nearly all visible color, and Roman buildings that once displayed vibrant pigments survive mostly as bare stone and plaster. Yet Tambo, Colorado presents a different story. Visitors today can still identify extensive sections of red, yellow, cream, and white decoration across walls, corridors, and ceremonial spaces. Archaeological analysis indicates that the pigments were primarily mineral-based. Red pigments likely came from iron-rich hematite, yellow tones appear linked to iron oxides and clay minerals, and white pigments were probably derived from calcium-rich compounds. The mystery is not where the colors came from, the mystery is why they remain. Laboratory studies show that mineral pigments alone cannot fully explain such preservation. Pigments require binders, and without a binding agent, wind erosion, temperature fluctuations, and occasional rainfall events would gradually remove them. Researchers have proposed several possibilities. Organic binders derived from plant extracts, cactus compounds, animal proteins, or natural gums may have been used. The problem is that many organic substances decompose over centuries, leaving little trace for modern scientists to analyze. This creates a remarkable archaeological puzzle. We can see the results of the formula, but not necessarily the formula itself. The environmental challenge makes the mystery even greater. Although the Peruvian coast is extremely dry, it is not completely stable. El Niño events periodically bring heavy rainfall capable of damaging adobe architecture. Seasonal temperature variations produce expansion and contraction within wall surfaces, while wind-driven sand continuously abrades exposed structures. Yet significant portions of the original coloration remain visible. Comparisons with other adobe civilizations are revealing. Many painted adobe structures associated with the Moche, Chimu, and Nazca cultures have suffered far greater pigment loss. Even where preservation is exceptional, the degree of visible color retention at Tambo, Colorado remains unusual. Some specialists argue that the answer may lie in a sophisticated combination of pigment chemistry, wall preparation, environmental conditions, and maintenance practices performed during the Inca period. However, no single explanation has yet solved the mystery completely. The colors of Tambo, Colorado continue to challenge assumptions about ancient material science. At first glance, Tambo, Colorado appears less technologically impressive than Machu Picchu or Sacsayhuaman. There are no gigantic polygonal stones weighing dozens of tons and no dramatic mountain terraces stretching across entire valleys. Yet the site's engineering achievements become increasingly impressive when examined closely. Unlike many famous Inca monuments, Tambo, Colorado was built primarily from adobe. Adobe construction sounds simple, but in reality it presents significant engineering challenges. Adobe bricks shrink during drying, crack when moisture levels fluctuate, and can develop structural weaknesses if mixtures are inconsistent. Large walls are particularly vulnerable to deformation over time. Despite these limitations, many walls at Tambo, Colorado remain remarkably straight. Angles are carefully controlled, corridors maintain consistent dimensions, and architectural symmetry appears repeatedly throughout the complex. Modern engineers understand that achieving such consistency requires careful control of material composition. The ratio between clay, sand, moisture, and organic reinforcement must be managed with precision. The question becomes obvious. How did Inca builders standardize construction materials across a large complex without modern testing equipment? No written construction manuals survive, and no engineering drawings survive. Yet the finished architecture demonstrates repeatable quality control. The knowledge clearly existed, but the documentation does not. Another mystery emerges from the site's geometry. Tambo, Colorado was not assembled randomly. The complex follows a highly organized layout consisting of plazas, ceremonial spaces, administrative rooms, storage facilities, and interconnected corridors. Such planning requires measurement. Today, architects rely on rulers, laser surveying equipment, GPS systems, and computer modeling. The Inca possessed none of these tools. Even more intriguing, they left behind no conventional writing system capable of preserving architectural plans in the way Egyptian, Roman, or Mesopotamian civilizations sometimes did. Yet the geometry is undeniable. Researchers believe the Inca employed standardized measurement systems, possibly based on body proportions, calibrated chords, or modular units used throughout the empire. Some studies suggest recurring dimensional relationships across multiple Inca sites separated by hundreds of kilometers. However, definitive evidence remains elusive. The architecture demonstrates measurement, but the measurement system itself remains largely invisible. It is similar to discovering a modern skyscraper while losing every blueprint used to build it. Peru sits along the boundary where the Nazca Plate descends beneath the South American plate. This geological collision generates some of the most powerful earthquakes on Earth. Over the past 5 centuries, the region has experienced numerous destructive seismic events. Entire cities have been damaged or rebuilt, colonial structures have collapsed, and modern buildings continue to require advanced seismic engineering. Yet Tambo, Colorado remains standing. The survival of the site raises important questions about Inca structural knowledge. Archaeologists have identified several potentially significant characteristics. Thick walls distribute forces more effectively, relatively low building heights reduce instability, and internal layouts divide structural loads among multiple sections, rather than concentrating them in single massive chambers. These features resemble principles recognized in modern earthquake-resistant architecture. Of course, Inca builders did not possess seismographs or plate tectonic theory. However, practical observation accumulated over generations may have produced engineering solutions adapted to a seismic landscape. This pattern appears repeatedly throughout the Inca world. At Machu Picchu, Ollantaytambo, and Cusco, structures demonstrate extraordinary resistance to earthquakes. Tambo, Colorado may represent a coastal adobe version of the same engineering philosophy. The Peruvian desert presents another challenge. Daytime temperatures can become intense. Solar radiation is powerful and water is scarce. Maintaining comfortable interior environments under such conditions is difficult even with modern technology. Yet many rooms at Tambo, Colorado appear designed to regulate temperature naturally. Thick adobe walls possess high thermal mass. During the day they absorb heat slowly, and at night they release stored energy gradually. This process reduces temperature extremes inside buildings. Researchers also note that doorway placement, corridor alignment, and courtyard organization may have encouraged natural airflow throughout the complex. The result resembles passive climate control systems used by modern sustainable architects. What is striking is that these solutions emerged centuries before the development of thermodynamics as a scientific discipline. The builders understood the environment well enough to shape architecture around it. Vallisana is a forgotten harbour on the western coast of Crete, Greece. Today its ancient docks lie stranded on dry land, several meters above sea level and hundreds of meters from the shore. That single fact has transformed Vallisana into one of the most remarkable engineering mysteries of the ancient Mediterranean. Unlike famous ports that vanished beneath the sea, Vallisana rose out of it. The site preserves an extraordinary snapshot of ancient harbour technology frozen in time, allowing archaeologists to examine not only how a major Greek port functioned more than 2,000 years ago, but also how its builders solved technical challenges that continue to puzzle researchers. The modern rediscovery of Vallisana began in the 20th century when archaeological surveys revealed unusual stone structures buried beneath farmland west of Crete. Excavations later uncovered harbour basins, fortifications, quays, warehouses, towers, and a narrow entrance channel connecting the harbour to the sea. What initially appeared to be a typical Hellenistic port soon became something far more mysterious. Geological studies demonstrated that the harbour had originally been built at sea level but was suddenly lifted approximately 6 to 9 meters during the catastrophic earthquake of 365 CE, one of the most powerful seismic events known from the Mediterranean world. The uplift preserved the harbour in a condition rarely seen elsewhere. Instead of being submerged and eroded beneath centuries of marine activity, much of its infrastructure remained accessible for direct study. The first mystery concerns the astonishing accuracy of the harbour's original design. Ancient engineers selected a location exposed to some of the most energetic wave conditions in the eastern Mediterranean. Modern coastal engineers understand that building a functional harbour requires balancing dozens of variables simultaneously: wave energy, sediment transport, prevailing winds, storm frequency, water depth, ship draft, coastal currents, and seasonal changes. Today, such calculations are performed using computers, satellite observations, hydrodynamic models, and decades of oceanographic data. Yet, the engineers of Falasana achieved a remarkably effective harbour design more than 2,000 years ago without any of these technologies. The entrance channel appears carefully positioned to allow access while minimizing direct wave penetration into the basin. The geometry suggests sophisticated empirical knowledge accumulated through generations of observation, but no surviving technical texts explain how such calculations were performed. The greatest engineering mystery of Falasana, however, may involve a problem that threatens every harbour ever constructed: sedimentation. Harbours naturally attract sediment. Waves transport sand along coastlines. Rivers deposit silt. Storms move enormous volumes of material across shallow seabeds. Over time, these processes gradually fill harbour basins and block navigation channels. Even modern ports spend millions of dollars annually on dredging operations to remain functional. Ancient ports face the same challenge but without powered excavation equipment. Falasana is particularly puzzling because it operated successfully for centuries in an environment highly vulnerable to sediment accumulation. Geological analyses indicate that the western coast of Crete experiences significant longshore sediment transport. In simple terms, enormous quantities of sand are continuously moved parallel to the shoreline by waves and currents. Under such conditions, harbour entrances can become blocked surprisingly quickly. Some modern marinas require maintenance every year. Yet Falasana remained an active commercial and military port for generations. Archaeologists continue debating how this was achieved. One possibility involves continuous dredging by human labour. Another proposes that the harbour's geometry was intentionally designed to create self-cleansing water circulation patterns. A third hypothesis suggests the builders exploited local current systems to reduce sediment accumulation naturally. None of these explanations fully account for the available evidence. This unresolved question becomes even more impressive when compared to other ancient maritime centres. The Roman harbour of Portus near Rome required massive engineering interventions and constant maintenance. The harbour complexes of Alexandria struggled with sedimentation throughout antiquity. Many Phoenician and Greek ports gradually became unusable due to silting. Falasana appears to have resisted these processes far longer than expected. If the harbour incorporated some form of passive sediment management strategy, it would represent a level of coastal engineering sophistication that remains only partially understood. The harbour entrance itself raises additional questions. Excavations revealed evidence of a narrow channel connecting the inner harbour to open water. Measurements suggest that its dimensions were carefully optimised. If the channel was too narrow, navigation would become difficult. If it was too wide, waves could penetrate the harbour and damage vessels. If it was too shallow, larger ships could not enter. If it was too deep, construction costs would increase dramatically. The final design appears to strike a balance between these competing requirements. Such optimization resembles modern engineering processes, yet no one knows exactly how ancient surveyors achieved the necessary precision. Equally mysterious is the apparent understanding of coastal topography demonstrated by the builders. Before constructing a harbour, engineers must possess detailed knowledge of underwater terrain. Modern projects rely on sonar mapping, bathymetric surveys, GPS positioning, and computer-generated models. Ancient engineers had none of these tools. Nevertheless, the placement of Phalasana suggests accurate assessment of seabed conditions, wave exposure, and navigational safety. Researchers still debate what methods Greek engineers used to collect and process such information. Rope sounding techniques certainly existed, but whether these alone could achieve the observed level of planning remains uncertain. The massive stone structures found throughout the harbour complex present another technological puzzle. Large blocks weighing several tons were quarried, transported, positioned, and aligned with impressive accuracy. Some retained stable positions despite centuries of earthquakes, storms, and environmental change. Structural engineers examining ancient Mediterranean harbours often emphasise that durability depends not merely on material strength, but also on load distribution, foundation preparation, and geometric stability. The survival of many Phalasana structures suggests builders possessed practical knowledge of these principles long before the development of formal engineering science. One of the most fascinating aspects of Phalasana is its role as a military harbour. Historical sources indicate that the city became a significant maritime power during the Hellenistic period. Protecting ships required more than walls. Effective naval defence demanded visibility, communication, logistics, and rapid deployment capabilities. The arrangement of towers and defensive structures suggests careful planning. Some researchers have proposed that visual signalling systems linked observation points across the coastline. Such systems existed elsewhere in the ancient world, but the precise configuration at Phalasana remains uncertain. If accurate, they would demonstrate a sophisticated integration of architecture, geography, and military strategy. The earthquake of 365 CE adds another layer to the mystery. Geological evidence suggests that Western Crete experienced one of the largest known tectonic uplifts in the Mediterranean during this event. Estimates indicate vertical displacement of several meters across extensive sections of coastline. The sudden rise effectively stranded the harbour above sea level and ended its maritime function. Yet, paradoxically, this catastrophe preserved evidence that would otherwise have disappeared beneath the sea. Modern archaeologists can walk through portions of the harbour basin, measure structures directly, and analyse engineering features rarely accessible at submerged ports. What do you think? Was Phalasana's long-term success the result of advanced harbour engineering, a lost sediment control technology, or centuries of accumulated maritime knowledge that has disappeared from history? Share your thoughts in the comments below. Mayo sits more than 3,300 meters above sea level in the northern Peruvian Andes, roughly 20 kilometers southwest of the city of Cajamarca. The site was first documented in detail by modern researchers during the 19th and early 20th centuries, though local communities had known about the strange stone canals for centuries. What immediately shocked archaeologists was not the scale of the ruins, but the engineering hidden inside them. Carved directly into volcanic rock was an artificial water channel stretching nearly 9 kilometers across mountain terrain, where such precision should have been almost impossible for a prehistoric society. Radiocarbon studies and ceramic analysis suggest that parts of the complex date to roughly 1500 to 1200 BCE, making the system more than 3,000 years old. That means Mayo existed long before the rise of the Inca Empire, and possibly even before many of the sophisticated hydraulic systems of the ancient Mediterranean world. Some researchers now classify it as one of the earliest known large-scale water management systems in the Americas. The first surveys revealed something even stranger. The canal was not built randomly downhill. Instead, it maintained an extremely controlled gradient over long distances, guiding water through harsh Andean rock formations with a level of planning that many historians did not expect from such an early civilization. The central mystery of Cumbermayo is the canal itself. The structure cuts directly through volcanic bedrock, sometimes only a few centimeters from steep drops and fractured stone surfaces. Even after thousands of years of earthquakes, seasonal flooding, and extreme weather, parts of the canal still function. Modern hydraulic engineers studying ancient water systems have pointed out that the canal's slope appears intentionally optimized. If the water moved too slowly, sediment would accumulate and block the flow. If it moved too quickly, erosion would destroy the channel walls. Yet Cumbermayo balances these forces with surprising precision. Some sections contain sharp zigzag turns that seem unnecessary at first glance, but engineers now believe these bends may have acted as primitive hydraulic brakes, slowing the water and reducing pressure damage during heavy seasonal flow. Similar concepts appear in much later hydraulic systems, including Roman aqueduct overflow controls and Nabatean water channels at Petra. Yet Petra flourished more than 1,000 years later. Researchers comparing the gradients of Cumbermayo to modern irrigation standards found that several sections remain within ranges still considered efficient for controlled gravity-fed water transport. The fact that prehistoric builders achieved this without iron tools, modern surveying equipment, or wheeled transport remains one of the greatest mysteries of the site. Another major puzzle involves the rock-cutting techniques themselves. Many canal walls display unusually smooth surfaces and remarkably consistent edges, while some channels form near-perfect angles inside extremely hard volcanic stone. Experimental archaeologists have attempted to reproduce similar cuts using stone hammers alone. While possible on a small scale, reproducing the long continuous channels of Cumbermayo would require enormous labour and exceptional planning, with some estimates suggesting tens of thousands of hours of coordinated carving. The mystery deepens because several surfaces appear polished rather than simply broken apart. Certain grooves are so straight that they resemble marks left by controlled abrasion techniques instead of random percussion. Researchers have proposed repeated grinding using quartz-rich sand, controlled water abrasion, heating and cooling the rock to weaken fracture zones, or the use of extremely hard hammerstones transported from distant areas. None of these theories fully explain the consistency seen across the entire canal network. Comparisons are often made with the granite cutting precision of ancient Egypt, the polygonal masonry of Sacsayhuaman, and the hydraulic tunnels of Persia. Yet Cumbermayo predates many of these achievements by centuries or even millennia. One of the most controversial theories surrounding Cumbermayo is that the builders may have intentionally redirected water between different drainage systems of the Andes. The site lies close to a continental watershed divide. Water on one side eventually flows toward the Pacific Ocean, while water on the other side feeds river systems connected to the Amazon basin. Some archaeologists believe the canal may have been designed to manipulate this natural boundary. If true, this would represent one of the earliest known examples of interbasin hydraulic engineering in the Americas. Such a project would require advanced understanding of seasonal rainfall patterns, elevation changes, flow pressure, terrain mapping, and long-term erosion behavior. Even modern engineers working in mountainous terrain rely heavily on precision measurements to avoid catastrophic water instability. The idea that a prehistoric Andean culture achieved a stable transfer system more than 3,000 years ago remains deeply controversial. Satellite mapping and terrain analysis conducted in recent decades have strengthened the argument that the canal's route was carefully planned rather than naturally formed. Perhaps the most difficult mystery to explain is durability. The Andes experience intense environmental stress, including rapid temperature fluctuations, heavy seasonal rain, strong winds, and seismic activity. Under such conditions, exposed stone channels normally degrade rapidly, yet many sections of Cumbermayo remain sharply defined after 3 millennia. Hydrologists studying the site observed that several channel sections appear intentionally designed to reduce turbulence. Curved walls and controlled narrowing points may have minimized destructive water impact. In some places, the rock surfaces are smoother than surrounding natural formations, suggesting deliberate finishing methods. The durability comparison becomes even more striking when placed beside modern infrastructure. Some 20th century concrete irrigation channels in Peru have required major repairs after only a few decades of erosion exposure, while portions of Cumbermayo have survived since the late Bronze Age. This has led some researchers to argue that the builders possessed a surprisingly advanced empirical understanding of long-term hydraulic stability. Cumbermayo may not have been purely functional. Surrounding the canal system is a strange volcanic stone landscape known as Los Frailones, filled with towering rock formations shaped like human figures, animals, and pillars. Some archaeologists believe the builders intentionally integrated these natural formations into ceremonial architecture. Petroglyphs carved into nearby rocks include zigzag patterns, animal figures, abstract symbols, and flowing line motifs connected to water imagery. Several carvings are positioned directly beside canal intersections, suggesting that water itself may have held sacred meaning. Anthropologists studying early Andean belief systems note that mountain water sources were often associated with fertility, cosmic order, and divine power. At Cumbermayo, the engineering may have served both practical and religious purposes simultaneously. Acoustic studies have also produced unusual findings. Wind moving through narrow stone corridors creates resonant tones and whistling effects that some researchers think were intentionally incorporated into ceremonial experiences. This transforms Cumbermayo from a simple irrigation site into something far stranger. A fusion of engineering, landscape manipulation, and ritual design. What do you think Cumbermayo really was? An ancient engineering breakthrough far ahead of its time, or evidence that lost knowledge once existed in the Andes long before recorded history? Share your thoughts and theories in the comments below. Ouidan el Faras, isolated in the desert north of Egypt's Fayum Depression, looks like little more than a bare basalt outcrop. Yet hidden among its black volcanic stone lies evidence of one of the most astonishing industrial operations of the ancient world. More than 4,500 years ago, during the age when the pyramids were rising along the Nile, Egyptian engineers developed a quarrying and transportation system capable of extracting thousands of tons of hard basalt from a remote desert and delivering it to royal construction projects hundreds of kilometers away. The mystery is not that the quarry existed. The mystery is how such a sophisticated logistical network functioned with a level of planning, surveying, and engineering that remains only partially understood today. The modern rediscovery of Ouidan el Faras transformed understanding of ancient Egyptian industry. Archaeological surveys conducted in the 20th century revealed extensive quarry remains scattered across the basalt plateau. More surprising was the discovery of an ancient paved transport road extending approximately 11 to 12 kilometers across the desert. Researchers eventually recognized that this was not an ordinary road. It may represent one of the oldest engineered freight roads ever discovered anywhere on Earth. Suddenly, Ouidan el Faras was no longer simply a quarry. It became evidence of a large-scale industrial landscape operating during the Old Kingdom, the same era responsible for monuments such as the Great Pyramid. The first puzzle begins with the basalt itself. Ancient Egypt possessed abundant limestone deposits close to the Nile Valley. Limestone was easier to quarry, easier to transport, and available in enormous quantities. Yet royal builders repeatedly chose to obtain basalt from one of the harshest and most inaccessible regions of northern Egypt. The decision suggests that ancient engineers possessed a sophisticated understanding of material properties. Basalt is significantly harder than limestone. On the Mohs hardness scale, limestone typically ranges between 3 and 4, while basalt commonly reaches values around 6. Its density often approaches 2.8 to 3.0 metric tons per cubic meter. The stone resists wear, survives heavy traffic, and maintains polished surfaces far longer than softer alternatives. Such characteristics made basalt ideal for temple pavements, ceremonial floors, and architectural elements subjected to constant use. The question is how ancient planners evaluated these advantages thousands of years before the emergence of modern geology or materials science. The quarrying process itself presents another unresolved mystery. Basalt is notoriously difficult to work. Modern quarries frequently rely on steel tools, explosives, hydraulic equipment, and diamond cutting systems. Ancient Egyptian quarry workers possessed none of these technologies. During much of the Old Kingdom, copper remained the primary metal available for tools. Copper is substantially softer than basalt. Archaeologists generally believe workers used dolerite hammerstones to fracture the rock and employed quartz-rich sand as an abrasive during cutting and shaping operations. Experimental archaeology demonstrates that such methods can work, yet scale remains the challenge. Widan el-Faraz was not producing a few ceremonial objects. Evidence suggests sustained extraction on an industrial level. Thousands of tons of basalt appear to have left the quarry over centuries. The mystery is not whether ancient workers could cut basalt. The mystery is whether the known techniques can fully explain the speed, efficiency, and production volume implied by the archaeological record. Equally remarkable is the logistical system hidden behind the quarry. Widan el-Faras lies in an environment that receives little rainfall and offers few natural resources for large groups of workers. Every quarry operation required food, water, tools, replacement equipment, shelter, and transportation. Maintaining such an operation would have demanded careful planning and administrative coordination. Comparisons can be made with Roman imperial quarries, such as Mons Claudianus in Egypt's eastern desert. However, many of those Roman operations were established nearly 2,000 years later and benefited from administrative systems that are much better documented. At Widan el-Faras, the organizational mechanisms remain largely invisible. The workers are gone, the records are scarce, only the infrastructure remains. The most fascinating mystery surrounds the ancient transport road itself. Archaeologists discovered a carefully engineered route connecting the quarry to the shores of the ancient Lake Moeris region. The road crossed difficult desert terrain and appears specifically designed for hauling heavy stone loads. Unlike ordinary pathways created through repeated use, this route required planning before construction began. Engineers had to identify a corridor capable of supporting repeated transport of multi-ton blocks while minimizing risk and energy expenditure. This immediately raises one of the greatest unanswered questions in ancient engineering. How did Egyptian surveyors map the landscape? Modern route planners rely on topographic maps, satellite imagery, aerial photography, GPS systems, and computer modeling. Ancient Egyptians possessed none of these tools, yet the route selected at Widan el-Faras demonstrates a sophisticated understanding of terrain. excessive gradients would have made transport impossible. Soft surfaces could trap sledges. Sharp changes in elevation would dramatically increase labor requirements. Somehow, ancient surveyors identified a viable route across kilometers of desert while optimizing for efficiency. The methods used remain poorly understood. Some researchers proposed that teams conducted systematic ground surveys using simple sighting instruments, measuring ropes, and observation points. Others suggest generations of accumulated practical knowledge allowed ancient planners to recognize optimal terrain intuitively. Yet even these explanations leave questions unanswered. Modern engineering studies show that hauling heavy loads often requires careful calculations involving friction, slope, load distribution, and traction. The transport route at Wadian el Faras appears too effective to be the product of random trial and error alone. The challenge becomes even more impressive when the properties of basalt are considered. A block measuring only 1 cubic meter could weigh nearly 3 metric tons. Larger architectural blocks would weigh considerably more. Experiments involving ancient-style sledges indicate that moving such loads requires substantial manpower. Research conducted on ancient Egyptian transport methods suggests that reducing friction through water lubrication can significantly decrease pulling forces. Famous tomb paintings show workers pouring water ahead of sledges carrying colossal statues. Whether similar techniques were employed at Wadian el Faras remains uncertain, but the scale of the operation strongly suggests advanced knowledge of mechanical principles. Another puzzle emerges from the unfinished blocks still scattered across the quarry. These abandoned stones provide rare snapshots of the production process. Tool marks reveal stages of extraction. Partially detached blocks show how quarry workers separated stone from bedrock. Yet, some unfinished pieces appear so large that their intended transport remains difficult to explain. Their existence raises the possibility that engineers occasionally push technological limits beyond what available infrastructure could reliably handle. In some cases, abandoned blocks may represent failures. In others, they may reflect changing construction priorities or political disruptions. The archaeological evidence does not provide definitive answers. The transportation chain extended far beyond the desert road. Once blocks reached the lakeshore region, they likely entered a river-based distribution network connected to the Nile. From there, stone could be shipped to royal building projects throughout Egypt. This process required coordination between quarry workers, transport crews, boat operators, administrators, and construction teams. The logistical complexity rivals systems associated with much later civilizations. Comparisons can be drawn with Roman imperial supply networks or the movement of granite from Aswan. Yet Wadian el Faras predates many of these examples by more than a millennium. The road itself also challenges traditional assumptions about the history of infrastructure. Historians often associate engineered roads with civilizations such as Rome, whose vast network eventually stretched over 400,000 kilometers. Wadian el Faras demonstrates that specialized transport roads existed far earlier. While much smaller in scale, the road's purpose was highly sophisticated. It was not built primarily for communication or military movement. It appears to have functioned as dedicated industrial infrastructure. In that sense, it resembles a prehistoric freight corridor designed exclusively for moving raw materials. The Nile deserts of northern Sudan hide the pyramids of Nuri far from the crowds of Giza, rising from the sand like broken black teeth. More than 80 pyramids stand here, a royal necropolis of the Kushite kingdom built over 2,500 years ago. Some are small and shattered, others still dominate the horizon despite centuries of erosion, earthquakes, floods, and looting. Yet the greatest mystery is not why they were built. It is how a civilization with far fewer resources than Egypt engineered structures and underground tomb systems so advanced that parts of them still cannot be fully explained by modern archaeology. The site was first documented in detail during the 19th century by European explorers traveling south of Egypt. Later excavations revealed that Nuri became the burial ground of Kushite kings after the reign of Taharqa, one of the most powerful rulers of Nubia and Egypt combined. Archaeologists quickly realized this was not simply a copy of Egyptian pyramid culture. The engineering methods at Nuri were different. The geometry was different. Even the underground structures followed patterns unlike those found beneath most Egyptian pyramids. At first glance, the pyramids appear smaller than those at Giza. The Great Pyramid of Khufu originally stood around 146 meters tall, while the largest pyramid at Nuri likely reached around 50 meters. But the Kushite builders compensated with steeper angles, often exceeding 70 degrees. That made construction dramatically more dangerous. In structural engineering, steeper slopes increase lateral pressure and raise the risk of collapse. Yet many pyramids at Nuri remained standing for more than 2 millennia, despite being built with less durable sandstone and rubble cores instead of massive limestone blocks like those used in Egypt. Modern engineers studying the site noticed something unusual in the foundations. Beneath several pyramids are compacted layers of crushed stone and sand acting almost like primitive shock absorbers. Similar concepts are used today in seismic base isolation systems to distribute force and reduce stress during ground movement. No written Kushite engineering manuals survive, yet the builders somehow understood how to stabilize massive structures on terrain affected by seasonal groundwater changes from the Nile. Satellite imaging and geological surveys show the underground water table around Nuri has shifted repeatedly over thousands of years. Under such conditions, most ancient mud brick structures would have fractured or sunk. Many of the Nuri pyramids did not. But the real mystery begins underground. Beneath the pyramids lie burial chambers connected by long descending stairways and tunnels cut directly into bedrock. Some passages extend more than 20 meters below the surface. Today, many are flooded by groundwater, making exploration extremely dangerous. In 2019, underwater archaeologists used scuba equipment to enter submerged chambers beneath Taharqa's pyramid. What they found raised even more questions. The tunnels were astonishingly straight. Laser measurements showed some corridors deviated only a few centimeters over long distances carved through stone. Achieving that level of alignment without modern surveying tools is extremely difficult even today. Ancient workers supposedly used bronze chisels, stone hammers, ropes, and oil lamps. Yet the geometry suggests an understanding of spatial planning far beyond what historians once assumed about Kushite engineering. Even more puzzling are the tomb ceiling systems. Several burial chambers contained massive stone blocking mechanisms designed to permanently lock the tomb after burial. Unlike simple sealed doors in many Egyptian tombs, some chambers at Nuri appear to have used sliding stone barriers hidden within narrow shafts. Archaeologists discovered grooves carved into walls where multi-ton stone slabs could descend into place with remarkable precision. In some tombs, the entrance corridors narrow sharply before widening again deeper underground, creating spaces where large blocking stones could be maneuvered and dropped into exact positions. The engineering problem is enormous. Some blocking stones likely weighed several tons. Moving them underground through confined tunnels without cranes or iron machinery would have required carefully calculated force distribution, ramps, lubrication systems, or counterweights. Yet no surviving diagrams explain how this was done. Attempts to recreate similar systems experimentally have shown that even small errors in angle or friction would jam the stones permanently before reaching their final position. What makes the mystery even stranger is the precision of the grooves themselves. In some chambers, the channels guiding the stone blocks are cut with unusually smooth surfaces and nearly symmetrical dimensions. Archaeologists comparing them with Egyptian examples noticed that certain Nuri grooves appear more mechanically refined, despite the Kushite kingdom having fewer known resources than New Kingdom Egypt. Some researchers speculate that wooden sled systems combined with wet clay lubrication may have been used. Others believe hidden sand-release chambers could have acted like primitive hydraulic braking systems, controlling the descent speed of the stones. No consensus exists. Then there is the question of labor organization. The Pyramid of Taharqa alone may have required tens of thousands of tons of stone. Transporting that amount of material across desert terrain under temperatures exceeding 40 degrees Celsius would have demanded extraordinary logistics. Ancient inscriptions suggest Kush controlled major Nile trade routes and had access to gold wealth from Nubia, but economic strength alone does not explain the engineering coordination. At Giza, archaeologists found evidence of massive worker villages, bakeries, and supply chains. Comparable infrastructure around Nuri is far less visible, suggesting the Kushites may have relied on a different and possibly more mobile labor system. The astronomical alignment of the pyramids adds another layer of mystery. Many structures face roughly north-south, but not with the exact orientation patterns used in Egyptian royal pyramids. Studies comparing stellar alignments suggest the Kushites may have used different stars as reference points, potentially adapting their system to the southern skies more visible from Nubia. Some alignments appear connected to the rising positions of specific bright stars during the Kushite era around 700 BCE. If true, the builders possessed advanced observational astronomy without leaving behind detailed written records explaining their methods. Even the stone-cutting techniques remain controversial. Certain chamber walls display parallel cutting marks so regular that some researchers initially suspected later modifications. However, dating confirms many were original. Experimental archaeology has shown bronze tools can cut sandstone effectively, but reproducing identical grooves with ancient methods requires enormous time and skill. Some cuts inside Nuri chambers are so narrow and straight that maintaining them by torchlight underground would have been extraordinarily difficult. Then came the flooding. Over centuries, rising groundwater invaded many burial chambers. Some tunnels collapsed, others disappeared beneath dark subterranean lakes. Yet the flooding may ironically have preserved parts of the site from looters. Radar scans indicate there are still unopened voids beneath several pyramids. Entire chambers may remain untouched. That possibility has transformed Nuri into one of the most important archaeological mysteries in Africa. What do you think is still hidden beneath the flooded pyramids of Nuri? Could there still be untouched chambers waiting to reveal lost engineering secrets? Share your thoughts in the comments below. Dreros is ancient, windswept, and almost forgotten. High in the mountains of eastern Crete, Greece, roughly 600 meters above sea level and overlooking the Gulf of Mirabello, the ruins of Dreros occupy a rugged landscape that seems poorly suited for urban life. Yet, nearly 3,000 years ago, a thriving city emerged here. What survives today appears modest compared to Knossos or Athens, but archaeologists increasingly recognize Dreros as one of the most important laboratories for understanding how advanced technological knowledge survived the collapse of the Bronze Age. The mystery is not simply who lived here. The mystery is how a relatively small community developed engineering, metallurgy, surveying, administration, and architectural techniques, whose sophistication remains only partially understood. The site first attracted scholarly attention in the late 19th century, but major excavations during the early 20th century revealed something extraordinary. Beneath collapsed walls and layers of stone debris emerged evidence of one of the earliest Greek cities of the Iron Age. Archaeologists uncovered temples, civic buildings, inscriptions, retaining walls, reservoirs, and some of the oldest known bronze cult statues ever discovered in Greece. Each discovery answered one question while creating several new ones. The deeper researchers examined Dreros, the more difficult it became to explain how much technical knowledge had survived after the collapse of the Minoan and Mycenaean worlds several centuries earlier. The first puzzle appears before a single building is examined. It is the location itself. Dreros was constructed on steep, uneven mountain terrain. Modern engineers understand the difficulties involved in creating stable urban infrastructure on slopes. Gravity constantly pulls foundations downhill. Seasonal rains accelerate erosion. Earthquakes destabilize retaining walls. Yet the ancient builders transformed this challenging landscape into a functioning city. Large terraces were cut into hillsides. Public spaces were leveled. Residential districts were organized along controlled elevations. Stone retaining walls distributed enormous loads across unstable terrain. The precision of these modifications raises important questions. Surveying instruments as we know them did not exist. There were no laser levels, satellite positioning systems, or modern measuring equipment. Yet many of the city's structures exhibit alignments that suggest systematic planning rather than gradual, uncoordinated growth. Researchers estimate that some retaining systems moved thousands of tons of stone and soil. Even more remarkable, portions of these systems survived nearly 3 millennia in one of the most seismically active regions of the Mediterranean. Crete sits near the boundary between the African and Eurasian tectonic plates. Throughout history, powerful earthquakes have repeatedly struck the island. Ancient cities were damaged, rebuilt, and sometimes abandoned entirely. Yet many walls at Dreros demonstrate surprising resilience. Their construction techniques reveal a sophisticated understanding of structural behavior. Instead of relying solely on rigid masonry, builders often employed layered stone arrangements that distributed stress through multiple points of contact. Small stones filled gaps between larger blocks, creating flexibility with an apparent rigidity. This principle resembles earthquake-resistant techniques later observed in Inca architecture at Machu Picchu and Sacsayhuaman. The civilizations were separated by oceans and more than 2,000 years of history, yet both appear to have discovered similar engineering solutions. Whether the builders of Dreros consciously designed for seismic resistance remains debated, but the evidence suggests practical knowledge gained through generations of observation and adaptation. Nothing at Dreros, however, has generated more fascination than the Temple of Apollo and the remarkable bronze statues discovered within it. The temple itself appears relatively modest in scale, but its contents transformed scholarly understanding of early Greek metallurgy. Excavations revealed 3 hammered bronze figures representing Apollo, Artemis, and Leto. These statues date to approximately the late 8th century BCE and rank among the oldest large-scale bronze cult images ever found in Greece. At first glance, they seem simple compared with the masterpieces of classical Greece produced centuries later. Closer examination tells a different story. Metallurgical analysis reveals controlled manufacturing processes requiring significant technical expertise. The bronze sheets were carefully shaped, joined, reinforced, and assembled into coherent anthropomorphic forms. Achieving this required precise control of temperature, alloy composition, hammering techniques, and structural support systems. The challenge becomes apparent when compared with modern metalworking principles. Bronze typically melts between approximately 950 and 1050 degrees Celsius, depending on composition. Maintaining consistent temperatures without modern furnaces, thermometers, or controlled fuel systems demands extensive practical knowledge. too little heat and the metal cannot be shaped effectively. Too much heat risks structural damage and oxidation. The craftsmen responsible for the Dreros statues operated within narrow tolerances despite lacking scientific instruments. Even more intriguing is the historical timing. These statues appear during a period traditionally associated with recovery from the Greek Dark Age. Conventional narratives often describe this era as a technological decline following the collapse of Bronze Age palace civilizations around 1200 BCE. Yet the Temple of Apollo suggests that significant metallurgical expertise survived. The question is how? Did technical knowledge pass continuously through local workshops? Were there forgotten networks of craftsmen preserving specialized skills? Or does the traditional model of cultural decline underestimate the complexity of post-Bronze Age societies? The mystery deepens when considering the broader economic system required to support such production. Bronze requires copper and tin, metals rarely found together. Tin sources in particular were often located hundreds or even thousands of kilometers from manufacturing centers. The existence of these statues implies participation in long-distance exchange networks extending across the Mediterranean. Somehow, a mountain city on Crete remained connected to technological and commercial systems far larger than itself. The famous legal inscription of Dreros introduces another dimension of complexity. Carved into stone during the 7th century BCE, it is often regarded as one of the earliest surviving constitutional laws in the Greek world. The inscription limits how frequently an individual could hold the office of kosmos, a senior civic position. While historians focus on its political significance, the technological implications are equally remarkable. Written law requires infrastructure. Someone must create standardized writing systems. Someone must preserve records. Someone must enforce regulations across generations. Such systems depend on literacy, administration, and institutional continuity. The inscription suggests that Dreros possessed organizational capabilities far beyond what many would expect from a relatively small Iron Age community. It represents not merely a legal document, but evidence of information technology in its ancient form. Urban planning offers further clues. Unlike settlements that evolved organically over centuries, Dreros displays signs of deliberate spatial organization. Civic spaces, religious structures, residential districts, and circulation routes appear integrated into a coherent design. This level of planning implies surveying techniques capable of measuring distances, establishing orientations, and controlling construction across large areas. Ancient surveyors likely relied on ropes, sightlines, plumb bobs, and geometric principles. Yet many details remain uncertain. Archaeologists can identify the final results, but rarely the procedures used to achieve them. This pattern appears repeatedly throughout ancient engineering. The structures survive, the manuals do not. Water management remains one of Dreros' mysteries. Despite its high mountain location and seasonal rainfall, the city survived for centuries, suggesting effective systems for collecting, storing, and distributing water. Archaeological remains indicate the use of reservoirs, cisterns, channels, and gravity-fed networks. However, much of this infrastructure has vanished, leaving only limited evidence of how the system fully operated. On a rocky hill overlooking the Mediterranean coast near modern-day Alicante, Spain, lies Tossal de Manises, the archaeological remains of ancient Lucentum. Today, visitors see weathered walls, fragmented streets, and scattered foundations. Yet beneath these ruins lies a puzzle that continues to challenge archaeologists. More than 2,000 years ago, builders transformed a strategic coastal ridge into a fortified urban centre that controlled trade routes, monitored maritime traffic, managed water resources, and defended itself against invasion. The city was not enormous by Roman standards, but what makes Toselde remarkable is the sophistication hidden within its design. The surviving stones suggest a level of planning, surveying, and engineering that appears surprisingly advanced for its era, while many of the technical methods behind its construction remain only partially understood. The site became widely recognized through archaeological excavations conducted during the 20th century, although references to ancient remains had existed much earlier. Located approximately 3 kilometers northeast of Alicante's historic center, the settlement occupied a naturally elevated position overlooking the Bay of Alicante. From this vantage point, inhabitants could observe approaching ships, monitor commercial activity, and defend one of the most strategically valuable stretches of coastline in southeastern Iberia. Archaeological evidence indicates that the settlement evolved from an Iberian community before becoming integrated into the Roman world. What researchers discovered beneath centuries of accumulated soil was not merely a collection of buildings, but a carefully organized urban system. The first mystery begins with the location itself. Modern geographic analysis demonstrates that Toselde occupies an exceptionally advantageous position. The hill provides visibility across large sections of the coastline while remaining close to agricultural land, freshwater sources, and maritime routes. Such a combination would be considered ideal even by modern urban planners. Today, geographic information systems can model visibility, transportation efficiency, and defensive advantages using powerful computers. Ancient builders possessed none of these technologies, yet they selected a site whose strategic characteristics remain impressive more than 2 millennia later. Whether this choice emerged from generations of accumulated local knowledge or from sophisticated surveying practices remains uncertain. The layout of the city introduces another fascinating puzzle. Excavations reveal evidence of organized streets, residential districts, public spaces, and defensive structures arranged according to coherent planning principles. Urban planning of this kind requires far more than simply constructing buildings wherever space is available. Streets must align with terrain. Drainage must function across multiple elevations. Defensive walls must integrate with the natural landscape. Every major structure must fit within a larger system. Archaeologists studying Lucentum frequently note the presence of recurring spatial patterns, suggesting that surveyors worked according to standardized measurements and predetermined plans. This raises an important question. How precise were ancient surveyors? Roman engineers are known to have employed instruments such as the groma for establishing straight lines and right angles. However, the surviving evidence at Toselde suggests a degree of consistency that still impresses modern researchers. Even small measurement errors become magnified when repeated across an entire city. Yet many sectors of the settlement display remarkable organization. Similar challenges appear at Roman colonial cities throughout the Mediterranean, but Lucentum presents an especially interesting case because its planners had to adapt their designs to an irregular coastal ridge rather than a flat plain. Balancing geometric order against difficult terrain requires considerable technical skill. The defensive system presents perhaps the most visually striking engineering mystery. Portions of the city's fortifications reveal a sophisticated understanding of military architecture. Rather than forming a simple enclosure, sections of the walls appear designed to maximize observation and defensive effectiveness. Angled segments, carefully positioned towers, and strategic sightlines suggest deliberate planning. Military engineers throughout history have understood that geometry can be as important as raw strength. A properly placed tower can eliminate blind spots. A carefully angled wall can expose attackers to crossfire. At Toselde, some of these principles appear centuries before the highly developed bastion systems of the Renaissance. Comparisons with other ancient fortifications are revealing. At sites such as Sacsayhuaman in Peru, researchers marvel at stonework precision. At the walls of Avila in Spain, attention focuses on the scale of the defensive circuit. At Tossal de Manasses, the mystery centers less on monumental size and more on intelligent integration between architecture and terrain. The city appears designed not simply to resist attack, but to exploit the landscape itself as part of the defensive system. Water management introduces another layer of complexity. Every ancient city depended on reliable control of water. Too little water threatened survival. Too much water threatened infrastructure. Coastal settlements faced additional challenges, including erosion, seasonal rainfall, and drainage across uneven ground. Archaeologists have identified channels, collection systems, and hydraulic features that indicate substantial planning. The remarkable aspect is not merely that these systems existed, but that they functioned effectively within a complicated topographical environment. Hydraulic engineering remains one of the least appreciated achievements of the ancient world. Modern drainage systems rely on precise calculations involving flow rates, gradients, sediment transport, and erosion control. Ancient engineers lacked modern mathematics and computer simulations, yet many Roman and pre-Roman hydraulic systems operated successfully for centuries. Similar mysteries appear at Petra in Jordan, where Nabatean engineers controlled flash floods, and at Machu Picchu, where Inca drainage systems continue functioning after 500 years. Tossal de Manasses belongs to this broader tradition of ancient hydraulic expertise that often exceeds popular expectations. Another unresolved question concerns construction logistics. Every visible wall required quarrying, transportation, shaping, and placement. The process demanded coordination of labor, materials, and engineering knowledge. Unlike modern construction projects, ancient builders lacked mechanized cranes, powered vehicles, steel machinery, and hydraulic lifting equipment. Nevertheless, large-scale urban construction occurred repeatedly throughout the Mediterranean world. The challenge becomes especially intriguing when examining the durability of surviving structures. Coastal environments are notoriously destructive. Salt carried by sea air accelerates deterioration. Moisture penetrates stone. Temperature fluctuations create stress within building materials. Yet portions of Lakentum's infrastructure survived more than 2,000 years. This longevity raises questions about material selection, masonry techniques, and environmental knowledge. Did builders understand which stone types would best resist marine conditions? Were construction methods refined through centuries of experimentation? Archaeologists can analyze the results, but reconstructing the exact decision-making process remains difficult. Trade networks provide another dimension of the mystery. Excavations have uncovered evidence connecting Lucentum to wider Mediterranean commerce. Goods, materials, and cultural influences arrived from distant regions. Such connections required navigation across open waters without magnetic compasses, GPS systems, radar, or accurate longitude measurements. Ancient mariners relied on celestial navigation, coastal landmarks, prevailing winds, and accumulated experience. Historians continue debating how precise these methods truly were, yet the archaeological record demonstrates repeated success. Trade functioned across hundreds and sometimes thousands of kilometers. The implications extend beyond economics. Long-distance commerce also facilitated the movement of technical knowledge. Engineering methods, architectural concepts, military innovations, and surveying techniques could spread through interconnected trade networks. Some researchers suspect that Lakentum may have benefited from this exchange of expertise, though determining exactly how knowledge traveled remains challenging. In eastern Crete, Greece, near the modern village of Kritsa, about 10 kilometers from the Gulf of Mirabello, the ancient city of Lato emerged through systematic excavations that began in the late 19th century. At first glance, the ruins appear less impressive than Knossos, Phaistos, or the great cities of classical Greece. Yet archaeologists increasingly view Lato as one of the most intriguing engineering puzzles of the ancient Mediterranean. Built between two steep rocky hills, roughly 300 meters above sea level, the city flourished from the 7th century BCE until the Roman period. More than 2,500 years later, researchers can map its streets, measure its walls, and analyze its reservoirs. But many of the technological systems that allowed thousands of people to survive and prosper in such a difficult environment remain only partially understood. The first mystery begins with the location itself. Ancient cities usually emerged beside rivers, fertile plains, or natural harbours. Athens had access to Piraeus. Corinth controlled strategic trade routes. Alexandria stood beside one of the world's most productive river systems. Lato had none of these advantages. Instead, its inhabitants selected a rugged mountain ridge with steep slopes and limited water resources. From a modern engineering perspective, it appears to be one of the least practical locations imaginable for a major settlement. Yet archaeological evidence shows that the city grew into one of the most important Doric centres of eastern Crete. Standing among the ruins today, visitors encounter an urban plan that appears remarkably organised despite the terrain. Streets, stairways, public buildings, defensive structures, and residential districts were integrated into the landscape with surprising efficiency. This raises an important question. How did ancient surveyors achieve such precision without modern instruments? Even small measurement errors would have multiplied across the steep hillsides, creating major structural problems. Instead, many terraces remain aligned after more than 2 millennia. Similar challenges can be seen at Machu Picchu in Peru or Monte Alban in Mexico, where builders transformed mountainous terrain into functioning cities. Lato demonstrates that Greek engineers possessed comparable abilities to reshape difficult landscapes through careful planning and surveying. Water presents an even greater mystery. Crete experiences long dry seasons, and Lato lacked direct access to a major river or permanent freshwater lake. Modern estimates suggest that a population of several thousand people would have required hundreds of thousands of litres of water each month for drinking, cooking, sanitation, and craft production. Archaeologists have identified large cisterns, drainage systems, channels, and collection basins throughout the city. These structures demonstrate sophisticated rainwater harvesting techniques, yet the complete hydraulic system remains uncertain. Some researchers believe undiscovered reservoirs may still exist beneath collapsed structures. Others suggest that groundwater sources were exploited using techniques that left little archaeological evidence. Whatever the answer, the city sustained itself for centuries in an environment where water should have been a constant limitation. The engineering of the reservoirs themselves creates another puzzle. Water storage sounds simple until one considers the technical requirements involved. Reservoir walls had to resist hydrostatic pressure, prevent leakage, and survive seasonal temperature changes. Even minor failures could contaminate supplies or destroy infrastructure. Laboratory analysis of surviving construction materials indicates careful stone selection and sophisticated mortar use. Similar hydraulic challenges were solved in other ancient societies, including Nabatea and Petra and Roman North Africa. Yet Lato achieved its solutions centuries before Roman hydraulic engineering reached its peak. The exact methods used by local builders remain incompletely understood. Stoneworking provides another remarkable mystery. Throughout the city, enormous blocks were quarried, transported, shaped, and assembled with impressive accuracy. Some retaining walls consist of stones weighing several tons. The challenge is not simply cutting the stone. The greater question is how those blocks were moved across steep mountainous terrain. Experimental archaeology demonstrates that moving multi-ton blocks even short distances requires substantial labor and coordination. Ancient Egyptian pyramid builders relied on sledges, prepared surfaces, and massive workforces. At Lato, the terrain was far less forgiving. No definitive evidence survives showing precisely how construction crews transported heavy materials from quarry sites to elevated building locations. The city's defensive architecture reveals additional technical sophistication. Lato occupied a naturally defensible position, yet its builders enhanced those advantages through careful design. Gates, walls, and elevated observation points created overlapping defensive zones. Modern military analyses suggest that attackers would have been forced into narrow approaches where defenders enjoyed clear tactical superiority. Similar principles appear in later fortifications such as Mycenae and even medieval castles. The mystery lies in the level of geometric planning required. Builders appear to have understood visibility, movement corridors, and defensive depth with remarkable effectiveness, despite lacking formal military engineering manuals. Earthquake resistance may be one of the most overlooked mysteries at Lato. Crete lies near the boundary between the African and Eurasian tectonic plates and has experienced destructive earthquakes throughout recorded history. Many ancient settlements across the eastern Mediterranean suffered repeated seismic damage, yet significant portions of Lato survived. Engineers studying ancient structures have noted the strategic use of bedrock foundations, thick retaining walls, and flexible construction layouts adapted to local geology. Similar empirical earthquake-resistant techniques have been identified in Inca architecture, Japanese castle foundations, and certain Roman structures. Whether Lato's builders intentionally incorporated seismic knowledge or arrived at these solutions through generations of observation remains unknown. The city's public architecture presents another unanswered question. The agora, administrative structures, and temples required levels of organization extending beyond simple construction skills. Building projects of this scale demand planning, logistics, resource allocation, workforce management, and long-term maintenance. Historians often focus on surviving monuments, but the true technological achievement may have been administrative rather than architectural. Every stone placed in the correct location implies systems of measurement, communication, supervision, and quality control. These invisible systems rarely survive in the archaeological record. Archaeologists have also been puzzled by evidence of economic activity that appears larger than expected for a mountain city. Pottery finds, imported goods, and trade connections indicate participation in wider Mediterranean networks. Goods arrived from regions hundreds of kilometers away. Maintaining such connections required transportation systems, storage facilities, accounting practices, and commercial coordination. Although no written records survive explaining these processes, the material evidence demonstrates that Lato functioned as part of a complex economic landscape rather than an isolated hilltop settlement. Scientific studies continue to reveal clues. Digital terrain modeling has helped researchers reconstruct ancient movement routes. Geological analysis identifies probable quarry sources. Hydrological simulations estimate water collection capacities. Architectural surveys generate highly accurate three-dimensional models of surviving structures. Yet despite these modern tools, many essential questions remain unresolved. Researchers can measure outcomes with extraordinary precision, but the practical knowledge behind those achievements has largely disappeared. Perched on a near-vertical rock fortress in the plains of Pamphylia, Silion was a city that somehow mastered water, stone, and survival, hundreds of meters above the ground long before modern engineering existed. Located about 30 kilometers northeast of modern Antalya in southern Turkey, Silion was known in ancient Greek and Roman records for centuries, but systematic archaeological surveys only intensified during the 19th and 20th centuries, as researchers began mapping the hidden ruins spread across the mountain summit. The first mystery of Silion is simple. Why build an entire city on top of an isolated stone mountain nearly 300 meters high? Unlike many ancient settlements that formed around rivers or fertile valleys, Silion sits on a steep rocky plateau with almost no natural advantages except defense. The cliffs surrounding the city are so steep that ancient historians described it as nearly impossible to conquer. Even armies moving through Anatolia during the campaigns of Alexander the Great reportedly avoided direct assaults on heavily fortified mountain cities like this, because the cost of attacking them was enormous. But defense alone does not explain the engineering challenge. To construct Silion, ancient builders had to transport thousands of tons of stone, timber, tools and food supplies uphill across rough terrain, without cranes, engines or steel machinery. Some retaining walls still standing today contain massive stone blocks fitted with unusual precision. In several sections, the gaps between stones remain incredibly tight despite nearly 2,000 years of earthquakes, erosion and weathering. Researchers often compare this style of tight polygonal masonry to sites such as Sacsayhuaman or Machu Picchu, because the stones appear carefully shaped to distribute force across uneven surfaces. While Silion was built by a completely different civilization, the underlying engineering principle appears strangely similar. Structures designed to survive instability by allowing energy to spread through interlocking geometry rather than rigid straight lines. That detail becomes even more shocking when considering the seismic activity of Anatolia. Southern Turkey sits near active tectonic zones, meaning these walls endured repeated ground movement for centuries. Yet parts of the city still remain attached to the cliff face with remarkable stability. The greatest unsolved engineering puzzle of Silion is not its walls or theatre. It is water. Ancient cities survive or die based on water access, and Silion should never have survived at all. The mountain summit contains no major natural spring capable of supporting a large urban population. Yet archaeological surveys uncovered enormous cisterns carved directly into bedrock, underground reservoirs, drainage tunnels, and sophisticated channels designed to collect and preserve rainwater with extraordinary efficiency. Some cisterns are estimated to hold hundreds of cubic meters of water. That alone is impressive, but the real mystery is precision. Water systems in ancient cities depended entirely on gravity. If a channel descended too steeply, flowing water would erode the stone and destroy the structure. If the angle was too shallow, water would stagnate or fail to move entirely. Modern hydraulic engineering uses laser measurement systems and advanced surveying equipment to calculate these gradients. The builders of Silion had none of these technologies, yet many surviving channels maintain slopes accurate enough to keep water moving steadily across difficult rocky terrain. This has led some researchers to compare Silion's hydraulic planning to the Nabatean systems of Petra. In Petra, engineers controlled flash floods and redirected water across desert cliffs with gradients so precise that modern studies found deviations sometimes measured only in millimeters per meter. Silion appears to show a similar understanding of hydraulic balance. The city's engineers also seem to understand long-term water preservation. Several reservoirs were coated internally with waterproof plaster mixtures containing lime compounds and crushed ceramics, materials known to improve resistance against leakage and bacterial growth. Roman hydraulic concrete using volcanic ash was famous for durability, but Sillion's mountain systems reveal that regional engineers may have adapted comparable methods using locally available minerals. Even more fascinating is the possibility that the city operated as a giant rain harvesting machine. The mountain's steep slopes naturally accelerated runoff during storms. Instead of allowing water to escape downhill, channels redirected it into storage chambers throughout the city. This means Sillion's survival may have depended not on a river, but on carefully engineered control of seasonal rainfall. That level of planning required advanced surveying, precise stone cutting, understanding of pressure and flow, and long-term urban resource management. In other words, this was not primitive engineering, it was systems engineering. Beneath parts of Sillion are underground chambers and carved passageways, whose full extent remains unclear. Some tunnels likely served military purposes, allowing defenders to move supplies or access hidden storage areas during sieges, but several carved surfaces raise uncomfortable questions for archaeologists. Some sections display unusually flat cuts and sharp internal angles carved directly into limestone. Reproducing those surfaces using only basic bronze tools would have been extremely slow. Iron tools were available later, but the consistency of certain cuts suggests highly organized labor and surprisingly advanced stoneworking methods. Experimental archaeologists have proposed multiple explanations, including heating rock with fire and rapidly cooling it to fracture surfaces, wooden wedges soaked in water to expand inside cracks, hardened iron chisels, or abrasive sand cutting techniques. Yet none fully explain the speed required to shape an entire fortified mountain city. At sites throughout the ancient world, difficult stonework repeatedly appears in places where civilizations faced extreme environmental challenges. The Incas shaped earthquake-resistant stone walls in Peru. The Nabateans carved entire structures into sandstone cliffs. The Romans drilled tunnels through mountains for aqueducts. Sillion belongs in that same category of ancient engineering that feels disturbingly advanced for its era. The remains of Sillion's theatre reveal another technical mystery: acoustics. Ancient theatres across the Greek and Roman world were famous for amplifying sound naturally, but Sillion's elevated location may have enhanced this effect even further. The curved seating arrangement, combined with reflective stone surfaces and the surrounding cliff geometry, created an unusually effective resonance chamber. Modern acoustic studies at ancient theatres show that certain designs amplified speech frequencies between roughly 500 and 4,000 Hz, the exact range most important for human vocal clarity. Builders clearly understood through experimentation that geometry could manipulate sound. At Sillion, the mountain itself may have functioned as part of the acoustic design. If intentional, this suggests the city's architects possessed sophisticated empirical knowledge of wave reflection centuries before the formal science of acoustics existed. Ancient records describe Sillion as extraordinarily difficult to capture. From the summit, defenders could monitor movement across much of the Pamphylian plain and nearby trade routes connected to the Mediterranean coast. This strategic advantage transformed the city into more than a settlement. It became a surveillance platform, military fortress, and emergency refuge combined into one. The mountain's steep sides acted like natural defensive walls. Attackers climbing uphill would exhaust themselves long before reaching the gates, while defenders above maintained visibility in every direction. Combined with large water reserves and internal storage systems, Sillion may have been capable of surviving sieges for extended periods. That raises another mystery. If the city was so defensible, why was it eventually abandoned? What do you think really caused the fall of Sillion? Earthquakes, water failure, or something historians still have not discovered? Share your thoughts in the comments below.